record on the. Good. Thanks a lot. So just to recap what we just did, in this lecture we're going to have a course on interpretable machine learning, and then we will have a lab about that in the second period. And the final period is going to be a bit more relaxed. So we will be speaking about how to read a research article. We will see this from 2 research papers, and then we will try to read one of the research papers that you guys choose on. The aim of this one is to basically explain to you how a research paper is made. So basically, what are the different components of research papers? What are the different steps in reading a research paper? And hopefully, using this information of how to read a research paper, you will be able to understand how to write a research paper, right? So understanding what are the different sections, what are the different key ideas that need to be presented in every section, or what are the ideas you need to look for in every section will help you write better articles, easier articles to read, and will speed up your work during your project. So let me just see how many students are here. We have 10 students, right? So I have 2 accounts. There are 10 students. That's good. That's good. And how many students in total do we have? We have in total around 18 students. So there are 8 students who are not joining. Probably they'll just watch it later on. Let's just give them the benefit of the doubt and wait a couple of minutes until they come. And for me, I'm going to just do something real quick and be right back. So that's good. I guess we were right. More people have joined. Let me see. I think I have a message. Nice. Yeah. First, I would like to thank everybody who already started working on their project. Yeah, sorry. I would like, as I said, to thank everybody who started working on their projects. Many of you guys have already contacted me with your ideas and we had one-on-one meetings. That's great work, you guys. I'm very happy about this progress you guys are making and the interest you guys are showing in the course. And for those who haven't started yet, I would just like you to know there's no pressure at all to start now or later. The goal of this course is to, well, teach you something that is useful. So far, many students have, so for example, the students from last year have just now contacted me saying that they are using exactly their project, the thing that they worked on in this course for example, job interviews and stuff. And that's the main goal of the course, right? So to give you something to talk about during your interviews, whether it is like a technical interview or just the first one, right? So usually the first interview where they just get to know you, and during these interviews, usually the person is just gonna try to see what are the projects you worked on, and having a research paper or just having a good project on GitHub will definitely start the conversation and keep the conversation going. And usually during the second interview phase, where you will be doing more of a technical, in-depth questions. If you have some GitHub code, usually they just open that GitHub code and start asking you questions just to make sure that you are the person who wrote it. And of course, if you are the person who wrote it, the interview will be very smooth and hopefully you will land the job you want, right? So yeah, other than that, I think we can directly start the lecture. So instead of doing the lecture on here, we're gonna start the lecture on the iPad. Again, I'm still trying to experiment with teaching, what is it called? Teaching with the iPad. Many students have told me it's much better to take notes and stuff. So let's go on the iPad and start preparing the lecture. Share content, screen, start broadcasting. You are now sharing your screen. Thank you. Oh, let's do something a bit different. Let's open OneNote. No. Yep. Here we are. Share screen again. Sadly, I still haven't figured out a solution to keep my camera on and do the presentation. So we're just gonna try to work that a little bit later on. So again, just for the sake of experimenting with teaching, for this lecture, we're gonna use OneNote. So it's just an app to take notes. And mainly because some students told me the annotations that we make on the screen during the lecture usually get completely deleted. So what I decided to do is to always give you the PDF of the lecture beforehand and the PDF that we work on together during the lecture and annotate, so add some drawings and stuff. We also save that and I will send it to you guys on Moodle after the lecture. I hope this will be a bit better. So today's lecture is going to be about interpretable machine learning. I'm not sure how familiar are you guys with interpretability or how important interpretability is, I'm assuming that you guys have not taken any course about this before, but if somebody has already taken it, then we can take it a bit to a more advanced setup. But given this lack of information, we're going to go with the following learning outcomes. So first we'll start, what is interpretability and what are the most interpretable models? What are the easiest models to interpret? And then we'll speak about LIME, which is a very cool method to explain very complicated models using a much simpler one. And then we go for GradCam, which is the most commonly used for image classification or just for image tasks in general, right? And just like a side note, for those who are looking for a research area, this is a very active research field, and I could give you a couple of ideas to explore for the sake of this course by the end of this lecture. Yeah, that final 1 hour and a half, you guys remember that? So that will be like a discussion for us. So the first part is going to speak about interpretability. So interpretability is the degree to which a human being can understand the cause of a decision made by your model, right? So for example, if you are applying for a loan in a company or in a bank, and the bank just says, no, the model did not accept your loan application, you would like to at least know why was your application refused. Maybe there are some things that you should work on, for example, income or your credit score or stuff like that, right? So now we're going to speak about what is interpretability and very important concept, which are the scopes of interpretability, right? So there are 5 scopes of interpretability, and I really hope that you guys remember these for the long term, because depending on what scope you guys would like to do, or what kind of scope, what kind of interpretability you would like to focus on, different areas of research would appear, right? And then, of course, we speak about the easiest interpretable models. I think here there's already like a very cool, well, the names are already there. So decision trees and logistic regression. So these are models that you can easily interpret. And I'm sure during the lectures with Professor Khan, he already explained to you how you can interpret the decisions of decision trees and logistic regression, right? So first, we would like to understand what is interpretability, right? So this is a screenshot from a paper that we recently published. And what it is saying is basically neural networks and machine learning models in general are very biased, right? Biased towards what? Towards the environment or towards the noise or the background of the image. So here, any human being can clearly see that this is a horse. So this is not something for debate, but the area around the horse. So this is, sorry guys, yep, here we go. So we can clearly see that this is like a desert, right? So this is something that is a desert, very commonly seen in Arabic areas, right? And what is also very commonly seen in Arabic areas are camels. So the model has decided that this image, since it is highly representative of this Arabic traditions, the image of a whole, or the image, the animal in this image is in fact a camel, not a horse. And this is a very clear mistake from our beautiful algorithm. And then after we apply this, what is it called? Interpretation on the model, we can clearly see that the model is focusing on things which are outside of the object, right? So he's focusing on this architecture instead of focusing on the object itself, right? So this is why we can see a lot of noise in here. But why is interpretability very important? There are many, many reasons. So the first one, it's to satisfy the human curiosity. So human beings are very curious creatures, and that's, I think, the main reason for our survival, right? We always like to question things and like to answer these questions. And interpretability will allow human beings to be curious about what the model is seeing and how the model is working. The second thing is to improve recommendations, right? So for example, if you are working in, or if you are building a recommender system, right? For movies, it's a bit easy situation, right? So even if you propose a movie that is not good, still it's not going to be the end of the world. But if you are in recommending, for example, a certain treatment for a cancer patient, right, based on their history, you would like to understand why did the model make such recommendations, right? The second, another thing is safety measures. So we would like to make sure that, for example, again, in the same cases where the models are making very important decisions, we would like to make sure that there are some, at least, measure of safety and understanding of this model. It's not just doing things randomly. We can trust this model. And another area of research where a lot of, like, especially here in Europe, a lot of research papers are coming, or a lot of research opportunities are coming in detecting biases in machine learning models. And usually these biases are against, for example, people of color, genders, and stuff like that. So a very good example was the use of AI for resumes. So let's just open this bracket here, right? So AI for scanning resumes. And basically what we're trying to do is we take the best at a certain field, and we teach the model to find similar resumes to these people who are the best in the field, right? So for example, I take the best, let's change the color because this is a bit depressive, right? Yeah, I take the best business people in a certain company, and I try to hire people who resemble them, right? So I'm trying to find resumes of people who are very similar to these ones. The problem is currently all the top people, or all the people who are in the top, are usually just white males. So if you train an algorithm on this data set, it's certainly going to have a lot of biases, right? So it's going to be biased towards accepting white people, white male people, instead of people of color, for example. And this is something that is very commonly researched, especially in like Europe and the US and stuff like that. And the final thing is to debug and audit the model. So once the model is being deployed, there's still some level of questioning for it. So you're always going to be auditing it and always going to be debugging it. And interpretability is the best way to go through that. Now, here is where things get a bit more interesting. For this one, I would like to just take a small pause and send you guys a very cool link that I think you should all have. And that is I just sent it on Telegram. Let me open it here locally. Or I can. Yes. Telegram. There it is. Okay. Share content, share screen, start broadcast. So this is a book about from an author called Christoph Molnar, and this is basically the book for machine learning and interpretable machine learning. It's a very good introduction to the majority of the best algorithms out there for interpretability, right? And here you will find all the information that you will need to understand this lecture and to basically answer questions during the midterm, right? So this book is a very short book. It's not like very complicated, but there are many parts in here that I would like you guys to read. And the most important parts is, for example, the scopes of interpretability. So the first one is algorithm transparency. And the best way to understand this scope of algorithm transparency is to ask the following question. How does the algorithm create the model? So for this one, oh, I didn't think this through. I thought I could annotate on this. Let me, nope, you cannot. Oh, yeah, sad I cannot annotate on it. Huh? Yeah, sadly I cannot annotate on it. But let's just go back then to the lecture, and you guys just keep the link open for you. So the first one is algorithm transparency, and in other words, this means how, or the train function. Do you know how the algorithm is being trained? So do you have access to the training function of this algorithm? Usually this is not something that you would easily get, especially for industrial models. So for example, you can't just ask how did Google train their models. So this is something that is too high to understand for us. But if it is a simpler model, such as, for example, linear regression, logistic regression, neural networks, all of these models, you already know them and you know how they are being trained. The second one is global and holistic model interpretability. And the best way to understand this one is to ask the following question again. How does the trained model make its predictions? To put it in simpler terms, do you have access to predict function? The third level, or the next level of interpretability, is global model interpretability on a modular level. A very weird name, but the main way to understand this is to ask the following question: how do different parts of the model affect the predictions, right? So the model is, for example, linear regression. Let's just draw it like this a little bit here. So for example, this is y equals this one. Let's use it with this ax plus b. So basically, do you know what are the different components of the model and how do they influence the prediction function, right? So usually if you already know the prediction function, you should see how these different parts interact with each other in order to give you the prediction. Now, the next level is where things get a bit more interesting. So this is the most important level of, or most important scope of interpretability, and it is local interpretability for a single prediction. So this one is, why did the model make a certain prediction for an instance? So for example, for this one, let's take it here. I don't know how to draw this one. You make loan application, and why was it refused? We will keep in mind this this idea of the loan application, because this is the idea we will continue with throughout the lecture. But this local interpretability for a single prediction is the most important one. And this is what we will be doing throughout the rest of the lecture. The last one is a bit less important, but it's, again, a very active area of research, which is local interpretability for a group of predictions. Just the same one in comparison for the loan applications. Instead of saying for this person, why was the loan like refused, you would ask something like, why was the loan refused? I think loan is not written like this, right? Loan, right? Okay, so this is how it's written. Why was the loan refused for people of color, right? So here the question becomes about a group of people instead of just one specific person. So these are the different scopes of interpretability. As we said, the first one is how was the model trained? The second one, how is the model making its predictions? The third level is how are different parts of the model interacting with the predictions? And the final two, which are the most important, I think, yeah. So why was the the final two, which are the local interpretability, either for one prediction or for a general group. Now we will start speaking about the most important things, right? So here I would just like it to be more of an interactive session. So I'm just going to ask you guys questions. Logistic regression, is it a very easy model to interpret? Yes or no?
Yes.
Nice. So it's a very, I don't know how to turn off notifications for this beautiful web. Nice. So it's a very easy model to interpret. Can the person who said yes, can they explain a bit further, right? So just tell me, what do they mean with easy to interpret, right?
Oh, I mean that you really only have one parameter that's laid out on an axis, and you see where the decision boundary lies. So you see which values, like which is the threshold value for a parameter for a decision to be made in the favor of one or the other class.
Right. So for example, if I'm making loan applications, so approve is a function of, let's say, income. Logistic regression would do something like this, right? So if income is bigger than 50K a month, then yes, else no. So it's going to be a bit more complicated, but if you simplify it into just a linear decision boundary, it's going to be doing essentially this, right? So this is for the case of just one value. Can somebody take this a bit further for something that is much more complicated, where we have multiple values and we're applying logistic regression on them? And what does it mean to interpret this logistic regression? Oh, wait, I could do this, right? Aha, since I'm already working with two laptops. So problem solved? Genius sometimes, huh? Okay, so let's continue, right? So what does it mean to have multiple values in logistic regression, and how does it influence this interpretability, right?
The more values you have as x, it became harder to interpret it.
Really? But we said it's easy to interpret, right? So probably there is something that is there to interpret. Let's just take it a very simple form, and we will have this: if y is bigger or equal than 0, true, else it's false, right? Now, y is a very complicated function, right? So y is a sigmoid function. We will ignore the sigmoid for now. It's a sigmoid function of what? Of plus b. So let's say we have 3 values. Can you tell me, remember this, what we said previously, right? How do different parts of the model influence the prediction? So try to make the interpretability, let's make it a bit bigger, based on the following. For some reason, it's not drawn. Oh, it is drawn, but it's weird. Anyway, So just try to make the interpretation based on the different components of the logistic regression. So what does it mean to have A1, let's say 1000, and A2 just 0.1, A3 0.2? What does it mean in terms of features importance, for example?
It means that the first feature is the most contributing to the result.
Very nice.
Specifically, it's a large amount of feature one corresponds to yes on the decision.
Exactly. So now using these different values, for example, for A1, A2, and A3, you can start speaking in terms of why is the model making its decisions. How? Because you already have the fixed value for X1, you have a fixed value for X2, and you have a fixed value for X3, because it's just one instance, right? So we already know these values. We already know the values for A1, A2, and A3. And what we just simply do, we give the what is it called? The user kind of a reason or like a graph that says this feature you should increase it a little more, this feature you should decrease it a little less, and this feature you should increase it, right? So for example, this is not 0.1. Let's take the example of this one being minus 1000, right? So this feature should be like completely taken down. So this is, let's say, a feature called the previous loans, how much the person is already in debt. So we would try to tell the person, reduce your initial debt first and then ask for extra loan, right? So this is how we interpret the results or the model of logistic regression. So now let's go back to the scopes and try to discuss, now that you already have this, right? So you already know all of these things. Can you guys tell me what is the algorithm transparency, whether we have the algorithm transparency, whether we have global holistic model interpretability, global model interpretability on a modular level, and the rest, right? So let's just discuss on each one of these parts. So algorithm transparency. Do you guys know how the logistic regression is being trained?
Yeah.
Yes. Next one is global holistic model interpretability. Do you guys know how the model is making its predictions?
Yeah, I guess.
Yeah, so it's just like multiplication and summation, right? So we know it. Now the next one is global model interpretability on a modular level. So remember, this means how are different parts of the model interfering or interacting with the predictions. As we said, just like take the example of this one being a very large positive value, another one being a very large negative value. So this way, this tells you that this feature is very important for the positive class, this feature is very important for the negative class. If something is very like 0.1, 0.2, this means it's a very useless feature and it's not really interacting a lot with our predictions. So this is the third level. Again, for the fourth level is exactly what we have said. And the fifth level, this is something that you can just try to come up with different ideas to work with it. So for example, you would try to gather all the, take the most important feature, say it's income, and try to find if this income feature is correlating heavily with some bias that you have found, let's say, or education, for example. Education is a very biased thing. So usually the people who get higher education are people of white people, especially white males previously. Now it's getting a bit more accepted, but still, if you use education or background as a feature, you could still find the model as being a bit racist and penalizing people coming from lower education facilities compared to bigger education facilities because they can afford to pay to study at Harvard, whereas the other one cannot afford that, right? So these are different ways to do it. Now let's try to discuss it, but for something a bit more complicated, such as neural networks. Do you guys know how algorithm transparency is working, right? So do you guys know how neural networks are being trained?
Yes.
Yeah,
Nice. So using what? Can you tell me?
backpropagation.
Exactly, right. So it's just back propagation and some loss functions, and magically everything is being trained. The next one is how are we doing the prediction function, right? So predicting is very simple. Again, we just put the input, multiply it with some weights, sum it, you get some different activations, again, multiply, do the summation, different activations, and again and again and again, until you get to a certain value. A very mysterious way, right? The next level is global model interpretability on a modular level. Now, this one is a bit interesting to get the opinions of the students about it. So what do you guys think? Do you know how the different parts of the model interact with the prediction?
If the model, like if the network is large, then probably no.
Yeah, if the network is very large, then probably no. If the network is very small, then it's just logistic regression, right? So as we have described in the last lectures, right? So,
Sorry, could you go back to the previous one?
mhm,
The global holistic model interpretability. Like,
yes.
is that in favor of neural networks?
No, it's against neural networks. This is not something that we understand in neural networks. This is what I'm going to discuss in here, right?
But
So here,
why? Like, technically, we understand that all is happening in neural networks is just a bunch of additions and multiplications. Like,
yeah,
why is this against neural networks?
this is pro for neural network. This is also pro, but this is a negative, right?
Oh,
So
so the
here,
second one is in favor of.
yes, the second one we already know it, right? We know how the model is making its predictions.
Okay.
We know the prediction function, but we don't know how each one of these values is making its predictions, right? So we come here, for example, this neuron is connected with this neuron with a certain weight. Can you tell me if this weight is influencing class dog positively or influencing class dog negatively? Very difficult, right? So this is something that we cannot easily do with neural networks unless we have some higher level algorithm for interpretability. We cannot do that easily. Next one is local interpretability for a single prediction. Can you tell me why did the neural network make its decision without having to put an algorithm behind it, right? So something very basic. Is there something very basic and direct for local interpretability for a single model, for a single prediction? Can you think of something, right? Maybe the income is too high, maybe the income is too low. You check the decision boundaries or something like that. Just throw ideas, guys, huh? No worries.
Sorry, can you repeat question?
Yes, so local interpretability for a single prediction, right? This means why did the model make its decisions for a single instance? So let's take, for example, a picture of a dog. Can you tell me easily why did the neural network classify this picture of a dog as a cat?
We can see the filters and the output of each layer. Like,
And what does that tell you, right? So you take each layer, you see its output, and what does that tell you, right?
see low feature, low level features, like how they combine together.
Uh-huh.
What are the final filters, and what are the model looking for on a picture to classify it as a dog.
So this is one way of doing local interpretability for a single prediction, but sadly, as you have described, it's pretty complicated task, right? So it's not something that is very straightforward. So here we're just gonna put a question mark, and we will answer this question mark by the end of this lecture. And the last one, again, as I said, so this is
Sorry, could I ask a question about this?
good. Yeah, there you go.
How is this different from the previous one? Like, if we know how each component contributes to the result of the prediction, then we know how the prediction was made, and vice versa.
Can you repeat the question? So again, so this one does not mean we know the prediction function. This means that we know, again, so this means that we don't know how each individual part of the neural network is influencing the decisions, right? So we don't know that.
No, I mean, like, it seems to me that the third and the fourth point are either always yes or always no together. It can be that one is yes and the other one is no. Because if we know how each component contributes to the result of the prediction, then we know why this prediction was made in the particular instance.
You are positive, you are correct in this question, right? So if you know, if it's positive, if the third level is positive, then the fourth level is always positive. But if the third level is negative, the fourth level can be anything you want. Okay, so let's take an example. Neural networks, we have no idea each weight, how is it influencing the prediction? But we can do something like this. So this is fourth level interpretability. So we can see the model is focusing on these pixels in order to make its decisions. So we can clearly interpret the results of the model, and later on we'll see it for text, for example. Text is a much easier thing to interpret, and we will see how neural networks are interpreting or how neural networks are working with text without understanding what exactly is happening to the text, right? So we don't know if this weight changed it positively or negatively, but we know that this word is the reason that the model has classified it as a bad review. So for example, if you have a review for a movie, you might not know how the weights of the neural network is reading the reviews, but you can clearly say that if the review says movie is bad, the word bad has clearly influenced the neural network to make its decision, right? So this is the fourth level of interpretability. It does not need the third level to be true for us to be able to interpret it. But what you just have said is very interesting, right? So because if you have the third level, fourth level is guaranteed, right? You're correct. Does that like answer the question?
Yes, thank you.
Nice. So now let's go to another algorithm and do a similar discussion, right? So this is decision trees. And decision trees, I think, are the easiest thing to explain, right? So first, how to explain a prediction on a certain sample. This is something that you guys should answer. Go ahead.
I'm not sure I understand the question.
Nice. So if I give you a decision tree and I give you an instance, so this is the decision tree, right? So this is a decision tree, right? Now let's imagine I gave you a certain instance. So this is person one data. And let's say after running the decision tree on this person one data, we find that he is here. So this is where the decision was made, right? So as you know, the leaves of the decision boundary represent its decisions. So here, for example, we say, no, do not give a loan. Can you tell the customer or the person who applied, why are we not accepting his loan application based on what you have in the decision tree?
Yeah, I guess yes. I mean, we can just go into the branches. We can just traverse the tree into the leaf.
Good. So you just give him the different conditions that are here, right? So this condition, and this condition.
Yeah.
Nice. Now let me ask you a more complicated question. What would you tell him in the report? For example, you give him a report. What would you say in the report for him to get a positive answer? So what should he change to get a positive answer? How can you write this report? How can you write this interpretability?
I don't
Hey.
think it's very very easy with this model.
Okay, go ahead.
Oh, that's it. I think it's difficult.
We
I
should
think
It's not very easy.
Huh?
we
Okay.
should just look at the paths for answer yes and see the difference between the customer
Uh-huh.
sample and
That's amazing, right? Perfect, right? So as your friend has said, it certainly does require a little bit of processing, but it's still intuitive, right? So if the person is here, this is the person, and he wants to go to class yes, we should just find the closest node which with class yes and tell him to just change that condition. So only because of this condition, he was classified as a no, right? So just because this one was not in his favor, his application was not accepted. So if he changed the value of this condition in favor of the yes, he would get his loan application accepted. So later on in the report, we would have to tell him either you fix this problem or you fix, for example, this problem, and you would give him different solutions or different paths towards going from here, from wherever he is, like here, to go to the closest yes answer or to a potential yes answer. So for example, you would tell him get better education, get a master's degree, or let's say increase your income first and then apply for such things, right? Or something like that, right? So each one of these decisions have influenced the model. So you would just tell him what are the different conditions, and he will have to work on that and apply again. Hopefully the model would send him to the yes.
I don't think this would be a very informative report because it doesn't really say which of the factors contribute more significantly than others. So for example, if we only tell the person, change this last third level node from no to a yes in order to get a loan, that might send them down a very difficult path, while they could have just like changed something up top and got a yes straight away.
Exactly.
And if the decision tree is large, we cannot just give algorithms of like 16 steps for every single yes in the tree.
True. So you would need to build something that measures the difficulty of the task. For example, just as you just described, right? So for example, this first closest answer is very difficult, but maybe something else up the tree is easy. So as you have said, we wouldn't just give him one potential road to change, but we would give him different roads. So this is the case for loan applications. Of course, in different fields, things might change drastically, right? So for example, if it's a cancer patient, you're not going to be telling him, if you just remove this organ, you're not going to, so things can be a bit tricky for changing the class of a prediction. But what we're saying is, theoretically, it exists, right? So the theoretical way of changing it exists, and this is the algorithm to do it. So, but a very, very good comment, right? The next one is something probably related to what you just said: how to measure the importance of a certain feature.
You can, but it feels like a heuristic of some sort. You
Go
can
ahead.
just kind of observe the tree and I don't know, maybe like see if a particular feature is always the deciding factor next to the leaf, then maybe that feature is more important.
Okay, let me ask you a small question. How is the decision tree being built? If you can answer this question, you will answer this question. What do we use as a measure to put feature 1 first, and then we put feature 4 in the second level? Can somebody tell me?
entropy.
Something information gain?
Exactly, information gain. And entropy, right? So information gain is calculated with entropy. Information gain is what will help you kind of understand the difference between or the importance of each feature. So theoretically, it exists, but again, one person would say the first one is the most important, and then these two are like the next most important, and then these three are the next most important, and stuff like that. Somebody else would say, I would stop directly at the start. Sorry. I would stop directly in the start. So in the first node, in here, you will calculate information gain for each one of these features. And basically, we just take the order of the first level or information gain. So this is another way of doing importance of features. And they're all good because there's no such thing as a correct answer in this case, but there's just one way of trying to understand them all, right? So we're just trying to answer a question for a human being, and any answer would satisfy that this question. So far what we have seen is, what is interpretability? Why is it very needed? What is the importance of interpretability? What are the different levels? And here we have seen 5 levels. And the last one was, what are the different easily interpretable models? So just to do a quick recap, can somebody tell me what are the different scopes of interpretability in a very simple manner, right? So the first level.
Do we know how the model is trained?
Yes, so train. Next one.
Do we
Go
know
ahead.
how the model makes its prediction?
So prediction. And the next one.
Do we know which features contribute more and which contribute less?
Okay, so feature contribution. Someone else? The last two are always very easy, right? So these are the things that everybody remembers. What are the next two? Don't be shy, guys. So people are very shy in this lecture. The next one.
So
Yeah.
what are these points?
What are what?
What are these? What are we like?
The
listing?
scope. Yes, the scopes of interpretability. So just to give you guys these guys. We're trying to list these guys. Can somebody remember the next one? These two go hand in hand and they're very easy to remember. What do you guys think they are?
Interpretability of a single prediction and of group of predictions.
Exactly. Single and group of instances. And these are the different scopes of interpretability. These are very important, and you're going to have lots of questions about these in the quizzes and in the midterm. So try to remember these ones, right? Do you guys need a quick break, or should we go for Lime and then take a break? Lime is a very simple model, so it's not gonna be too hectic for you guys. What do you think?
I'm fine with continuing.
Хорошо. So Lime is a very general purpose algorithm, and the most important thing you will know about this one is it is a black box interpreter. Black box interpreter means it's an algorithm that works for any algorithm, any model out there. You just give it the model and it will interpret the decisions of this model. Where is it being used? Where is Lime being used? Mainly being used in one case, which is, or the fourth level or fourth scope of interpretability. As we said, the fourth scope is what we will focus on during the rest of this lecture. So this is a black box model interpreter, and the name of it is the following: local interpretable model agnostic explanation. So model agnostic means black box, they're the same terminology, and local interpretable model agnostic explanations. This comes from the way of the algorithm works. So the algorithm is trying to explain a very complex model, such as neural networks, using a local simple model. We will see how the algorithm works in a few steps, and we will see how it's applied first to tabular data because it's the easiest example, and then how it is extended for text and images. So I will show you how it is extended for text, and then I will ask you how do you think it could be extended to images, and I hope you guys can answer that one pretty easily, right? So this one is up for you guys to decide. So very simple. So let's take this very big, complicated decision boundary, right? So you see this is a highly nonlinear decision boundary. Is that so, right? Everybody can agree that this is a nonlinear model.
Yep.
Nice. So this nonlinear model, we don't really want to understand the whole model as a whole. We just want to understand why did it classify this sample as a positive sample. This is the only question I'm interested in. So instead of trying to work with the model and get into the weights of the neural networks to explain this one, why not just approximate this neural network on a local part using a simple model, right? So why not just come here easily? If you take only this region, the model is no longer nonlinear. The model is a very simple linear model, right? So only in this region, only on a local region, the model is no longer very complex and the model is no longer very nonlinear. In fact, it is a very linear model, right? So as the more you zoom in a specific region, the more linear and simple the models tend to be. So instead of using the global model as a manner of interpretation, we will use an estimate of it, right? So what we will do, we will build a, sorry. So what we will do is we will build a linear model in this region, only on the few data sets or few samples around here, just to create some sort of an estimation of this global model, but on a local region. And this, what will this do? So basically it will tell us the following. The main problem is we don't have this decision boundary, right? So we cannot visualize this decision boundary. If we could visualize it, we can easily do the interpretation, but we cannot visualize it because it's in, let's say, 30 dimensions, right? So what we do is we estimate it using some linear model and just interpret this linear model. So you take this beautiful linear model, interpret this one instead, interpret local linear model. And from this one, we will get the answer that we are looking for, right? So if we just go very, very, very deep into this image and just zoom in into whatever area we're interested in, the model will tend to be linear, right? So this is the goal of this algorithm. If we would like to speak about it in different steps, the first one is to select our instance of interest. So this one is the first step. We need to select the instance of interest. Why? Because this is a fourth scope of interpretability. I have very good writing, right? Fourth scope of interpretability, which is a local single prediction explanation. So we select the instance of interest. Next, we generate fake data. So all of these points that you see in here on the right are just fake data, right? So this is just fake samples that we randomly select. In 2 dimensions, we just call numpy.random, and we just get a new data set of random values, as much as we guys want. And then we ask the model to make its predictions. Preferably, these points, random points, should be close to the point of interest. So what we do is we just sample randomly around this region. So we generate, randomly around this region, and try to use the model to make predictions on it, right? So what we do is for each one of these samples, so for example, this one, the model would say it's positive. This one, the model would say it's negative. This one, the model says it's positive. This one, it's negative. So we just take the predictions of the model as true labels. We use the predictions that the model has made as true labels, and we train a simple linear classifier. So here, this is the linear classifier that we developed after training basically a linear model on this randomly generated data. And the samples of this randomly generated data are the following, right? So the samples, the X is random. Y is the prediction of the model. Because we don't really care what is, we don't care about the true labels. What we care about is why did the model make them positive or negative. So we care about the results of the model more than the true value itself. So here, Y is the prediction of the model. And then we train basically. So we send this to, what is it called? sklearn linear regression, and we just give this the beautiful or logistic regression, right? And we train the model on this one, and ta-da, we will have our beautiful decision boundary. Now, one extra step, which is very important in this algorithm, is the following. Weighting, or is this one? Sorry. So basically weighting the new randomly generated samples according to their proximity to the instance of interest. So again, just to make sure that we are focusing mainly on the region of interest, what we do is we weight each sample depending on how far it is from the sample of interest, right? So for example, instances that are very close to our sample of interest will have a high weight, meaning they will influence the loss function drastically. So they will force the loss function to go in their direction. Whereas the points which are very, very far away will have a very minimal influence on the loss function or the loss values, right? And this is the algorithm. That's it. Very simple algorithm. You get this beautiful linear boundary that is created by the local model. And this one is just logistic regression, so you can easily interpret this one. If you would like to do, for example, decision trees or something like that, you could also do that. Nobody is telling you no. And instead of just interpreting logistic regression, you would just interpret a decision tree. So to recap, the algorithm does the following. First one is to select the instance of interest. The second is to generate random samples. The third step is to weight each one of these random samples depending on their distance from the instance of interest. Train any simple linear model on that newly created data set, and then explain the predictions of the global model by interpreting the local model. So this is a very simple algorithm. Does it work for neural networks? Yes. Does it work for, I don't know, sport vector machines, XJBoost, any algorithm you might think of, you can interpret it using live. Do we have any questions so far about this part?
Yeah. What if the point of interest is very far from the decision boundary?
Very good question, right? So in this case, what we will have is the following. Let's imagine it like this. So this is the point of interest. Let me just draw the decision boundary. It's here, right? This is the decision boundary. It's very far from the point of interest. But what we will have simply lots of points in here. Positive, 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 positive.
I'm sorry, the drawing is hardly
Very
legible.
small.
Maybe
Okay, like this?
you could take like a thicker line.
Thicker line, okay.
Yeah, much better.
It's like, let me just draw these randomly like this. And this one, let's make it a bit bigger, right? So there it is. Again, as we said, we will sample from all over the distribution of the data. Sorry. Right, so here we will sample very random points, but they will have very much small influence on the training. But regardless, even if you train on this one, even if the weights are focused on these, you would still find a good what is it called? Linear decision boundary that separates the negative classes from the positive classes. Even if it's very far from this decision boundary, you can still find it, right?
But wouldn't it just generate like a model that always says yes, for example?
Yes and no, right? So it will always generate a model that gets these classes, these points correct. So this is very, very important, right? So the main job for it is to get these classes as correct. So basically it will have a choice between, let's say line 1. So this is line 1. Let's say this is line 2. And this is line 3. Which one do you think has the lowest error?
Line 1.
Line 1, right. So line 2 has definitely the very highest error, something that the model would never even think of. Line 3, although it has very low error, but still we can improve. And if we can improve, we will improve because it's a very simple function, right? So it's a convex function. If it's a convex function, if there is something better, we will get it. So here, the model will certainly choose line number 1 and find the correct decision boundary, even if the point of interest is far from it.
Okay, I see.
Nice. Now, the next step is to see how can we apply this one for text data. So for tabular data, it's pretty simple as we have seen, but for text data, it gets a bit more complicated. Why is that? Because we have text, we don't have features. So text is something that is not fixed, right? So you can have very long sentence, you can have a very short sentence. The first problem that you will find is how do you generate more text, right? So how do you generate more these random points around the distribution? This is something that you cannot easily do. Another one is how do you interpret? What is interpretability for a model, for a text? And this will be solved with one simple answer. Lime expects vectors. Here we have text as input. In order to use Lime, we must find some method that converts text into a vector. If we have a vector, easy. Vectors, this is something that Lime works with all the time. Vector, we can just generate as many random data as we want. We can do anything we want, right? But for text, we don't have this ability to be vectorized. So this is step number 1. How can we make text into a vector? This is step number 1 that we would need to solve. Question number 2 is, how do we make predictions on this random data? So, right, so we generated these random vectors, but the original model does not understand vectors. The original model understands text. So from here, we will need to make step 2, which is from random vector, we need to convert it back into a text. This is the second question we need to answer. Can somebody give me some idea to solve question number 1? How can we convert a text into a vector? Throw out your most complicated and most intelligent ideas, and you will find that the idea is like very stupid and very easy. So the correct answer is the simplest thing you could ever think of. Let's take the following text, right? Movie is bad. Convert this one into a vector. What is like the simplest vector you could think of?
All ones.
Oh, nice. So 1, 1, and 1, right? So we have 3 features. Each word is a feature. And in this vector, we have all the words. Let's say the data we are generating, the random data we are generating is the following: 1, 0, 1. This is a random vector. Convert it back into a text. Movie bat. Done. This is text. Give it to the model. See if the model still makes the same prediction of negative review. So here the model is saying negative review. Here the model would probably say negative review because the word bad is here. Still negative. Another one that would be positive or neutral maybe. Movie is. If we give this one to the model would say neutral. So after lots of these random samples, the model, the linear logistic regression model, would start to pick up a small pattern here, right? A pattern that says the word bad is the reason we have a negative prediction. And this is exactly what the model is doing. So when I was teaching this course, for example, for master's students, they usually have courses on natural language processing. And whenever I say try to convert text into a vector, they always come up with these very, very crazy ideas and very smart ideas. For example, word to vec, we create a neural network that takes this one, maps it to a vector form. We create an autoencoder. So all of these ideas are very good, but the idea here is even simpler, right? So we're trying to build a simple model, and a simple model it is, right? So here's the simple model that we will be using for interpretability on text. So we take this, for example, next sentence: for Christmas songs, visit my channel. So can somebody tell me what is the thing that would, what is the word here that is very indicative for a spam? So for example, let's say Christmas, right? So not very related to spam because, your family would be like, hey, you should come over for Christmas and stuff like that. So this is not something that you would associate with spam. Song, some of your friends would say, you should definitely check the song out, not a spam word. Visit, you could just come over and visit your grandma or something like that. So it's not something very associated with spams, but my channel, this is something that is spam, right? So nobody's going to be interested in visiting your YouTube channel, in receiving emails from your YouTube channel. So as human beings, the second you see the word channel, you understand this is going to be a spam. So the model has done the same thing. The model has correctly classified this email as a spam. Let me reduce the size, just like this. Yeah. So what we do is we create a vector like this one. This is vector number 1. Vector number 1 contains all ones. So all the words exist. Now vector number 2, for example, is the following: 1 0 1 1 0 0 1. Can somebody tell me what is this sentence represented by 1 0 1 1 1 0 0 1?
Can you name the ones and zeros again, please?
This one, number 2.
For song, visit, and smiley face.
Yes, for song, visit, smiley face. Number 4, for example, does somebody can read number 4? Anybody?
Visit my channel.
For visit my channel, winky face, right? So already, just by looking at the data like this, you can already start seeing a pattern between the probability given by the model. So this is given by the model, and the word channel, the feature channel. So here we can see whenever the channel word is non-existent, we have a very small probability by the model. whenever the word channel is here, we have a very high probability. Now, this is the weight. This is the difference between this vector and the all once vector, right? So this is the difference between the original vector of the sentence and the randomly generated, what is it called? Randomly generated sentence. And what we will do, we will take these vectors as X. We will take these probabilities as Y. And this is the weight for the loss function, right? So these are the weights, sample weights for the loss functions. Have you already seen what are sample weights for loss functions? And how can you send it, for example, for logistic regression, for SVM, neural networks? In machine learning course, for example, have you done a lab on this one, sample weights?
I don't think so.
Okay, then just let's open the documentation of, because it will be very important for you guys to see this. Let's open the documentation of any model on sklearn. Classification. Sample weights are very important, right? Let's take something that you guys are already familiar with. Lasso, and this is for, no, classification. I want, yes, this beautiful one. Publish. Sample weights. This is class weights. This is for the importance of each class for a certain, for the classification. Feature sample weights. Let's see. Sample weight. No. Nope. Let's see. Sample weights. Some of them they already send it, but some don't, right? So let's see. Yeah, we just checked it. It didn't have it. Oh, we checked linear versus SVM, right? Maybe SVC in general would have it. Where's shrinking, class weight, decision function, random state? Yeah, they don't have it here too. Weird. Coefficient. If somebody can find it, that would be good. Still can't find it here. Compute sample weight. No, this is just to convert. A decision tree. Okay, for example, for decision tree, it is there. Can somebody give us the link for decision trees classifier? The decision tree classifier. It doesn't write it anywhere. Okay. Decision tree. Hopefully we'll find it here. Max features, random state, nope. Class weight, again, they don't put it here. I forgot, where do they put it? Let's see, here, scalar, neural networks, NLP classifier. Oh. Weight. Learning rate. Nope. No. Okay, so this is for the, but this is not for the training for some reason. They don't put it in the training. They only put it in the accuracy calculation. So let's go, for example, here to the sample weights. The definition is sample weights, useless. So let's see in PyTorch maybe. Nope. Sample weight by George. Yep. This looks like a good article where we can see, yeah. Weight for S sample, I'm not sure what S sample. A little bit.
When
So
you
here's,
search for weighted random sample,
yeah, waiting
with
for
the representation of the concept you want to find. Weighted
Okay.
random sampler.
random sampler.
Weighted random sampler by Torch.
Okay. Okay, this is one
Yeah, it's
that
forum post, but
inclusive
you may find, yeah, weighted random sampler. You can find it in documentation. Torch utils data sampler weighted random sampler.
That's good one. Weighted random sample. So this is the weighted random sampler, and basically it will give a higher probability for each instance to be repeated. For example, if you would like to focus more on that. What I'm speaking more about is the calculation of the loss function, right? So let's try to go back on the doc, and we're back here. So let's just come back here and describe it for us, because I want to see it in the loss functions, not just in the classes where they don't describe anything. So for example, the loss function of MSE, right? So this is MSE equals the 1 over n sum of y minus y hat I squared. So this is MSE. So what we usually do for, you can't see it, right? Can you guys see the text better now? Sorry.
No, it's still not that readable.
So this is, let's write it again. This is MSE is equal 1 over n of the sum over yi minus y hat I squared. Now, here we assume that all the samples have the same weight, which is 1 over n. If we have a weighted loss function, the MSE would look like this. The sum over weight I multiplied by yi minus y hat I squared. Meaning, for example, for a specific instance that you would not like to get wrong, the loss function would be too big, right? So if the model gets that specific instance wrong, the loss function would just increasingly jump, right? For example, the weight is 5,000. Let's just like exaggerate it, right? So the weight is 5,000 multiplied by this error, the error would be just huge. So this is what weights are used for. So weights are used to guide your loss function to make sure that specific instances get the majority of the focus of the model. So this is something that I assume you guys have seen in ensemble learning. Have you done ensemble learning with Professor Khan? I always forget.
I don't remember this.
Yeah, it's okay. If you haven't done it or you don't remember it, I'm sure Professor Khan has done it because he taught us this concept. But this is very important for ensemble learning, and especially for like sequential models that are learning after each other. This is also a very good area of research. But let's just come back here. And now, as long as you understand the basic idea behind using weights to change the loss function, basically the word or the instance that we would like to focus a lot on, we give it a very high weight, and the loss function would go in the direction of that instance. And the words that, or the instances that we don't care about, we give them a low weight, and the loss function would not care about them, right? So here, for example, we would have, this is the interpretability of the model, and it is called the feature weight. So here we can see, for example, the word is, good, a, Christmas, and song are not influential for the decision of being a spam. Sorry. Whereas the word channel has the highest feature weight, meaning that this word is the reason the model has classified it as a spam. And this is the interpretability part, right? So again, to repeat, to recap what Lime does for text, it simply does the same steps, right? So we select the instance of interest, we generate random data all around the field of that vector, and then we train a linear model on the weighted random samples with the predictions of the model, right? So this is just overall what is happening. Step by step, we take the text, map it into a vector. From this vector, we generate random samples. From these random samples, we bring them back into text, use that text for classification by the model, and there we go. We have our beautiful data set. This is the X for the training. This is the Y for the training, and these are the weights for the loss function. And here is how the results would look like. Now, let's stop here and open like a bracket to speak about Lime for images. Now that we have seen how is Lime being applied on text data, right? So we take a text. Let's go a bit smaller, right? Like this. Can you guys see it? Still?
Yeah, I guess. Still, like a thicker line would be more desirable.
Okay, let's go like this. I should not use this color. Text into a vector, and then vector into text. The key components or the key characteristics of this vector, it must be small. Why? Because if we have a very large vector form, linear regression is not going to be trained very well because it suffers from the curse of dimensionality. So preferably the vector should be very small and it should be effective, right? So it should allow for the conversion from text and back to text. Now let's go and do the same thing for images. So it should allow for the conversion from image to a vector, and then from a vector to an image. Can somebody tell me like the easiest way to do this, which is?
Pixel by pixel.
Flattening, right? Exactly what you just said, right? It's called flattening. Flattening an image. So basically we take it from this shape into a vector form like this. Very, very, very long array. Idea works very well, right? So pixel by pixel, each one of these values would contain 1, right, for the existence of that value, or 0 for the not existence of that value. Train a logistic regression, and there you go. You should have it. If you apply the solution, you're going to find a problem, which is the curse of dimensionality, right? The curse of dimensionality. So this is the problem that we would have with that idea. So we would need something very similar to flattening, but that gives you something smaller. So try to think of an idea to combine these pixels, right? Have you done moving mean? No, I forgot the name. There are some clustering algorithms that do a very good job. And I forgot the name of the algorithm. sklearn clustering. Mean shift, yep, mean shift. Do you guys know mean shift?
No.
Let's take a look at it, right? I think there is a cool way here to insert online pictures. Let's hope for it. Mean shift. There it is. So what mean shift does is just basically tries to look at the data. It's like k-means, but it doesn't have the problem of specifying k beforehand, right? So it just basically tries to find the places where the majority of the samples are located. So here, for example, we start with a point in this area. What we do is we take the mean over all the points in this region. So preferably we have this R as a, what is it called? A hyperparameter of the model, right? So we start from a random point, put a circle around it, and then move the center to the mean of that circle, or to the mean of the points in that circle. Again, we repeat it again and again and again until we reach the place that has the highest, well, the center of basically of the distributions, right? The places with the highest concentration of points. So this is the idea of mean shift. But what I'm more interested in, I'm not sure if you guys have done this in clustering lectures, but the most important part of mean shift is its applications. Its applications on images are wonderful. They're just amazing, right? So it would take an image like this one, and it would cluster the pixels of that image. So for example, this is cluster number one, clouds. We have clouds in here. They would just cluster all the points of the clouds into one cluster. This is another cluster for another cloud. This is cluster called sun. I don't know, this is cluster door. This is cluster house. This is the application of mean shift. There are many other clustering ideas that work very well for images. So what we do is basically create the following. Something called as superpixeling, right? What superpixeling does is just creates different clusters of points or regions with similar colors. So any group of pixels which are connected together and are similar in colors will be grouped in the same cluster. So here is the result of superpixeling. Again, this is just another clustering technique. There are many, many techniques to do superpixeling. There are many algorithms to do this. There are algorithms specifically for images. So they're not just general learning clustering techniques, but there are specific algorithms for superpixeling that are not clustering techniques. But as we have said, it could be thought of as just another clustering algorithm for pixels of an image. So as we said, we just cluster the pixels of this image. And now we have region 1, region 2, region 3, region 4, region 5, region 6, 7, 8. So we can count them. Of course, they will be a lot. It will be, let's say, 100 regions. But 100 regions compared to 1048 times 1000. I don't know what are like the dimensions of images nowadays, but it's pretty huge, right? So this is not some vector that you would send for linear regression. But a vector with 100 features, this is something that linear regression still can work with. And this is what the linear regression would do. Sorry, the logistic regression would do, or LIME would do. So LIME would take an original image, superpixel it, then from those superpixels, it would just create vectors. The vector, again, is just a binary vector. Superpixel 1 exists or not, superpixel 2 exists or not, superpixel 3, superpixel 4, exists or not. And then you have the vector, you have a way to map it back into an image. So this image will be sent for classification. Now you can easily generate something similar to this one, right, for different images. And you will have the following. This looks exactly like the image that we started with, right? Remember, so the image was telling us these regions are interesting for the model to make its predictions. These regions were not interesting for the model to make its predictions, right? So if this region was removed, the model still did not change his decision. But when this region was removed, the model has changed its decision drastically, meaning this region was very important. And this is basically how we apply LIME for image data. So now I would just like to ask you guys, do you have some questions? If not, then we could just take a small break and come back to finish GradCam. GradCam is a very simple algorithm again, but it will require some fresh heads, right? Any questions?
I don't understand if, like, because the way we are applying LIME for text and images seems very naive. Like,
Yes.
text and images are very contextual data forms, so we
Yes.
cannot just remove parts.
Yes,
Like, does that not matter in this case, or
it
how does
does
that
matter, and it's not an optimal solution, right? So this is not something that will work perfectly. This is something that will work in most cases. So something that will give you some sort of understanding of the model, right? So why is it very good? It's a bit fast. It's not very fast. It's very slow actually, but it's a bit fast, and it does not make any assumptions on the model, meaning it's very widely applicable. And instead of, for example, having to show your model to others, you would just, for example, if some company, external company, third party company is trying to investigate in your software or in your model, you wouldn't have to give them the model or the code of the model. You would just give them an ability to interact with the model, and they wouldn't be able to see what the model it is, right? So the model is still being treated as a black box. This is a very important feature. Of course, the less assumptions you make, the less accurate your results will be, but it's still something that we are willing to pay the price for. So for example, in text, when we removed the word movie is, so this sentence makes no sense, right? So this is one of the problems of it, right? When we remove some words, sentences make no sense. So the idea itself is not very optimal, but still it does give a certain level of interpretability, and it keeps the model hidden from the user, and that is a very big bonus for us. Same thing here, for example, depending on the super pixeling technique that you have used, you might get some very different results from line, right? So if you, as I said, there are many super pixeling techniques. If you combined this region, so for example, if it was not broken like this, but it was broken like this, you might have a completely different output from line. And this is just because of the super pixeling technique that you have used, right? So just how did you group the pixels together? Another problem would be these super pixeling techniques are not smart algorithms, these are heuristics, right? So for example, if you are a human being and you are wearing a, what is it called? A helmet, the color of the helmet for some reason was similar to the color of a car in the background. Super pixeling technique would take your helmet away from you and put it in the car. And basically any interpretation that you will do after that one would be completely useless, because if you are, for example, focusing on the helmets, now the helmet is always completely gone with the car, and your interpretability model is going to start telling you the car is the reason for the model's predictions, but in fact, it's not, right? So these are very like common cases, and they happen a lot. Lime is not an optimal algorithm. It is, in fact, an algorithm with many, many problems, but the most important part of it is that it is black box, and black box is very important these days. Does that answer your question?
Yes.
Nice. So your question is amazing, and the answer to your question will be in the next slides. Basically, this one will not treat the model as a black box. This one is going to go into depth about the model. But so far, what we have seen in the lecture is what is interpretability, why are we using interpretability, and what are the 5 scopes of interpretability. We have seen some interpretable models, and we've seen LIME for tabular data, for text, and for images. Next, after the break, we will do GradCam, which is an algorithm for images, and specifically for CNN-based models. So for now, let's just take a small break and come back like, let's say 20, right? So take a 10-minute break. Okay? See you guys soon. Oh boy. Oh boy. Bash. Stop broadcasting. Nice. No queue. Yeah, can you guys hear me now?
Yes.
Nice. So let's continue our lecture. And now we will speak about, do you guys have any questions so far about what we have seen? Nothing? So if I ask again, what are the different scopes of interpretability? Can you guys name them? Yeah. Well, it should be very easy, right? So go ahead, guys. Anybody remembers the scopes of interpretability?
Do we know how the model is trained?
Nice,
Do we know how the model makes its prediction?
nice.
Do we know what features contribute most and what features contribute less?
Yeah, more or less, nice. The last two?
Do we know for a single item, data item, how the decision was made, and for a group of items, how the decision was made?
Very well. So now we will speak about another method for the fourth level or the fourth scope of interpretability, which is single instance, let's say local single instance interpretability. And this algorithm is called GradCam. So GradCam is a popular technique for creating class-specific heat maps based on a particular input image and a trained convolutional neural network. So what it does basically, you give it an image, let's say the image of a dog. Here's a dog. And basically it will make a certain decision. The CNN will make its decision. What we will get is the explanation of why the CNN made any class probability, right? So the CNN does not just give you one decision. It doesn't just say it's a dog or it's a cat, but it gives you like a vector with a probability for each class. So for example, the data set or the model has correctly classified this instance as a dog. So for example, here it was 0.4. But sadly, we see that 0.3 was given for a probability of 0.3 was given by the model for a class cat, for example. And we would like to understand, why is the model confusing cats and dogs? And for that, we could use GradCam to basically go deeper into why did the model, why did the CNN make any decision it has made, right? So if it made the decision for cat or a dog or any other class, we could choose whichever class we want and investigate that class specifically. So this is what class-specific heat maps look like, right? So for example, we chose the correct class in this case, which is a specific type of dogs. I don't know what is the name of this dog, but it looks like a beautiful dog. So why did the model make its decisions on this beautiful dog is because of these regions which have high activations, right? So here we have the red areas means influential, whereas blue areas mean non-influential, right? These also contributed a little bit, but mainly it is the eyes and the nose of the dog that made it obvious. In the start of the lecture, when we asked about this part, somebody made a very, very good algorithm on how can we use local interpretability for single prediction for neural networks. Is this person still online, and can he repeat his algorithm? Because the algorithm that he described is actually very close to the algorithm of GradCam. So can you repeat the idea that you just described? If you're still online, of course. Have you dropped out? I think it was Maxime or something like that. Yeah, certainly they have dropped out. That's it. So, well, let's just, I really wanted to have this discussion actually, because the idea that he said is actually very close. So hopefully if you're watching the recording, try to map your idea back into GradCam. And if you have a different way of doing things, maybe you could end up with doing research in this field. So the algorithm in itself is very simple. So basically, you guys remember CNNs, they take an image, this is the image, and then they send it through a classic filter, right? So this is our filter. The activation of a CNN, for example, here, this is the activation function. In this area that had nothing of interest to the, let's say to the, what is it called? Had nothing interesting for this classification. So it didn't find anything for its filter. So for example, all of these areas would be just zeros, but it picks up a certain feature in this region, right? So we already have this notion of heat maps throughout the entire CNN architecture. So let's try to build the CNN again together. So this is, okay, let's use a bigger. Here we go. So this is a CNN. This is layer 1. Let me find if there are some cool visualizations for visualization for CNN activations. Not what I'm looking for. Just trying to find a cool visualization for what the neural network is seeing, or what are the patterns that the neural network is picking up. For example, here. Can you guys see my screen here?
Yes.
Okay, nice. So here you can see that the neural network these are the activations for different kernels, right? So of course, at each layer, you're going to have multiple kernels. Each one will give different activations. And let's say that this filter has, or this kernel has activated in the areas close to the nose. This other one has activated close to the face. This one has activated close to the eyes and stuff like that. So imagining the following, maybe let's do it on a whiteboard like this. So imagine the first layer, right? So number 1 is learning or trying to find some very lower level features, right? And then layer 2 will try to build on these features to get something more. Layer 3 will build on that for something even better. Layer 4, for example, is the last one. This is the higher level feature extractions, right? So this one, what it will give you? It will give you different activation feature maps for different very interesting concepts, right? For example, this one, I'm saying, this one is the activation created by the kernel that is picking up on face, right? So whenever this kernel has found a potential face, it would activate. Whenever it did not, it would just turn it off. Same thing, we will have another filter, for example, in the last layer that is working on combining these lower level features in order to find, let's say, the eyes of a dog. So here we can see that we will, in the final layer, we will generate, let's say, 64 different feature maps. Each feature map is, let's say, useful for a certain class, right? So the first feature maps, let's say the first 3 feature maps are used by the model to detect features for the human face. The next 3 feature maps are used, for example, to detect features for the dog. The next one are used for detecting features, let's say, for the dog and a horse, like the common features between these two. This is what each one of these activation feature maps is looking for. So they're looking for some higher level information. Of course, when the image contains a face, all of these eyes of dog filters, right? So this filter that is looking for eyes of dog would not have any activation. It would be just completely filled with zeros. Same thing for the one looking for horses, right? So it would be completely built with zeros. So what we can do is just combine all of these filters, just like do the summation of all of these filters, and you would have some sort of heat map of interesting. Let's now go back to the iPad. It will be easier to write. Sure. Whiteboard, right? Yeah. So as we said, the final layer would be giving us different activation feature maps useful for different application areas. The first one, for example, would say face. The next one would say dog. This one would look for cats, something high level, right? So each one of these features or each one of these activation maps given by the final layer, of CNN, they are trying to find higher level concepts useful for the classification. So now I'm using something like face and dog, but in reality, it's not really finding these, it's finding something specific for the CNN, but for our purpose of understanding, we will use these concepts. So as we said, we could just combine all of these different values and we will get a heat map of interesting locations in the image, right? So for example, this pixel in the feature map is generated from, this is original image. So this is the original image, right? Original image. This pixel is generated from this region in the original image, right? So this is the region of area that was later just condensed with CNNs and max pooling and gave us 1 pixel here. So if this pixel is turned on, this means that the CNN has caught interest in this particular region. If it's turned off, the CNN completely ignored this region. It didn't find any interesting features in here. Same thing, for example, in the center. If this center point has very high activations, that this means this region was interesting for the CNN. Now, the twist on it that we can add extra information is, how can we make it class specific? How can we ask the neural network, what features did you use to understand exactly or to classify exactly this image for this class? How can we get this idea? Let's, oh, we can make another one. Wow, genius idea. Okay, so how can we make it class specific? So now we will look at the second part of the CNN, right? So first part we saw is the encoder. Right, let's come back here. So this is the encoder part of the CNN. We're only working on the encoder part. Now let's go to the classifier part. So the classifier part will take something like these. So it takes different feature maps. And then it will just flatten all of them. Just flatten everything, make it one single vector like this. Map it after a couple of multi-layer perceptrons, right? Just some linear activation, some fully connected layers. And it would give you the final prediction per class. Can somebody tell me, how can we calculate a measure of, for example, for this value, how can we calculate the effect of any of these different pixels on this value. This is something very commonly seen, for example, for gradient descent, right? So for the algorithm of gradient descent, it calculates the loss, and then it tries to calculate a proxy for how influential was this value or was that neuron for the loss function. Can you think of the same thing, but instead of like loss and neuron, we're thinking of value in output, probability of output, and a pixel in a feature map. Using the same technique, right? What is this technique? It gives you like a proxy of the influence of that value for this specific probability value or value, right?
Backpropagation?
Yes and no. Can you tell me what is important about backpropagation? What is it calculating?
It's calculating the effect a particular input,
Yes.
let's say data point, had on all of the chain, like on the entire chain of neurons.
And effect is equal to what in mathematics?
Coefficient?
Yes. How is backpropagation calculating this effect?
Derivatives, like gradients?
Yes, the gradients, right? The gradients, they give you some sort of an estimation of how much was this value, you can't see it, how much was this value influenced by this value. This is what derivatives will give you. Now let's combine these two ideas, right? So first we have a feature map that tells you what are the interesting regions in the image. And then you have a way of calculating how interesting each value in these feature maps is for that class. So instead of previously what we were doing, right? Previously, we were just doing the sum. Now we can improve this sum using an extra information, which is the weight of influence for that class, right? So we can calculate how influential was this whole filter for that specific class. Can somebody tell me how can we do that? With our idea here, we can calculate for this value to every single pixel in the filter map, in this feature map. How can we combine all of these different values? Let's make a new one. So we have this. We have this beautiful image. Each one of these pixels represent the influence or the gradient of that specific pixel for that specific class, for class C. How can we combine all of these values into one single value that says influence of filter number 1? It's a very simple technique that you're already familiar with. How can you summarize a group of values into one value?
Convolution?
Something much easier. Let's say, for example, I have the grades of all the students. How can I say one value that kind of represents all the grades of the students?
Average?
Average, exactly. So I just take the mean over all of these gradients, right? So all of these gradients represent the influence of each one individual pixel for that specific class. Now what we will do is we will calculate the average of all of these, and this will give us the influence of all pixels on that class. So now that we have this beautiful idea laid up, let's continue our lecture. And now we will be able to understand GradCam much easily. Yeah. Anyway, so here we said we have our beautiful CNN. Here it is. it is extracting features from the input image, finding interesting regions in the image, interesting activations. These are the list of interesting activations that we have. And what we do is we just calculate basically, or we make the weighted sum of all of these final feature maps, because the final feature maps represent the feature maps with the highest level of abstraction, right? So they're not the lowest level features like small face, small nose, or edge of the nose and stuff like that, but it's the whole face. So that's what we're hoping for, right? And that's basically what we will do. So we will sum all of these. We will take the average of all of these, but not just any average. We will take the weighted average. How do we calculate the weighted average? Basically, each one of these pixels in each one of these filters will have a gradient with regards to this tiger cat, or for example, class C. That will give us exactly the same size as this one, right? For every pixel, there is a gradient. So we will have lots of windows. What we do is we summarize each one of these different matrices into just one value by taking the mean. And this value will represent, let me zoom in. Yep, this value will represent the weight of this first filter on the classification for that class. And basically what it will give you is this GradCam activation. We follow that by just a ReLU activation just to remove all the negative values. But ReLU, as you guys know, is just a like non-linear kind of linear activation function. So it's just removing the negative values. Anything that is like too negative is still considered just 0, right, for us. And we're more interested in the positives instead of the negatives. So here we get the feature map for, or the heat map for the activations. And you will notice that this image is very pixelated compared to this image. Why? Because convolutions and max pooling reduce the size of the input, right? So input, then the output will be smaller than the input, then the next output will be smaller than the previous output, and smaller and smaller and smaller. So basically the size of these convolutional feature maps will be much smaller than the size of the original image, meaning if we would like to get them back in the same shape, we will just do something called as upsampling. And when we upsample, things will be a little bit pixelated, as you guys can see here. So just to put it in algorithmic steps, first one is to compute the gradients or the influence of every single feature map for that specific class. And how do we do that is basically combining, calculating the gradients for YC. This is prediction for class C with respect to the feature map activations number K. For example, this is the activation number K. Activations are all in the final layer. So in here, for example, we might add L for final layer of convolutions, but it can be done for any other layer, so there's no problem. But as we said, the best results usually come from the final layer. Basically, IE is the derivative of YC with regards to AK. What we do then is we will have another group of, these are just gradients. These are the calculated gradients for this one. And there's just lots of matrices. And what we do is we take the global average pool. We just take the average of all of these different matrices. And that will give us the importance of a certain feature map for the classification for class C. So it's importance of feature map K for class C, right? Final step is very easy. We just take the weighted average of the different feature maps and send them through our beautiful ReLU function, and we get this beautiful results. So this is how we make the activations for, or the calculations for GradCam. Do you guys have any questions so far? Because I have lots of questions for you. Any questions? GradCam is a very simple algorithm, right? It's very intuitive once you think of it, right? So the first one is to understand that these convolutional feature maps represents what the model thinks is an interesting area right? So any activation, any number one, anything positive in the activation feature maps or the convolutional feature maps represents something that the model thinks is interesting. And then we can find what the model thinks is interesting for that class just by calculating the average, by weighting the average using this information from the gradients, right? So the information from the gradient, as we said, represents the importance of that value to that class, right? So combining these two values or combining these two concepts of interesting for model plus useful for class C. If you combine these two ideas together, you get GradCam. So hopefully all of you guys understand what is or how does the model compute what is interesting, and you understand how can we measure what the model finds useful for a certain class. If you guys don't have any questions, then I will have some questions for you, and that is in terms of speed, which algorithm do you think is better? Lime or GradCam? So which one is faster? Remember, so Lime, what it does, it will generate random data, right? And then make a classification for each one of these random data, and then train a linear decision boundary, a linear model, and then interpret that model. Whereas for GradCam, we're calculating the gradients and we're making a summation. So which one is faster?
I would say GradCam is faster.
GradCam is 10,000 times faster, right? So it's a million times faster. Why? Because Lime, as we said, works only if we have lots of samples. So for example, we generated 1,000 samples. 1,000 is not enough, right? So 1,000 is very small. We have generated 1,000 samples. For each one of these samples, we will send it for prediction by the model. So each one of them will be an inference on the CNN, making it a very, let's say one inference costs like, I don't know, a lot. Let's say one inference costs 1 second, for example. So it's 1,000 seconds just for calculating the Ys. Whereas for GradCam, only thing that is a bit heavy in calculations is the calculations of gradients. And the calculations of gradients really don't take a lot of time. It takes similarly enough time as what inference would take. So let's say 1 second, right? So a rough comparison would say that Lime is 1,000 times slower than GradCam. And of course, GradCam is faster. It gives better results. So now we're working with something that is much better. That is something that is learned. We're not combining pixels based on how our super pixeling technique is doing it, but we're combining them based on a learning technique. So we're combining them based on the weights of a neural network that was trained for that specific data set, right? Super pixeling techniques, they're just heuristics that work for everything. And as we have seen in the introduction to computer vision, heuristics that work for everything tend to not give very good results for edge cases, right? So this sums up our lecture on GradCam, our lecture on model interpretability. So we spoke about interpretability, what it is, where do we find it? We spoke about what is the importance of interpretability and why it was a very active area of research. We spoke about the 5 scopes of interpretability. Each one of these scopes can be a research field, especially the last 3 values, the last 3 scopes. And we spoke about the different interpretable models, which are logistic regressions and decision trees. After that, we spoke about Lime for tabular data, for text, and for images. And then final thing, we spoke about GradCam for images. Now, one small question is the following. Is GradCam model agnostic or not? So is it a black box interpretability method, or is it a white box, open box, something like that?
Open box.
Yes, correct. I think you guys have understood very well. So this is it for the lecture. Do you guys have any more questions? If there are not any more questions, then I will just go quickly through the this one. Yeah, just to tell you guys what are the parts that you should focus on in this book. So this is the book that you will find most of the questions coming in the, for example, exams and stuff. I will make most of my questions from here. So the first one is just speaking about his life. And then he will speak about interpretability in general. So the importance of interpretability, this is something that will motivate you guys to read about interpretability and research about interpretability, but this is not something for questions. So this is not something I would use for question material, but for those who would like to understand what interpretability is and do research on it, importance play a role for motivating them, right, to work on it. Then here is just the taxonomy of interpretation. This is a very important concept, and this is something that I will ask lots of questions about, but I will not teach. Here is the scope of interpretability. Again, this is something that I will ask a lot of questions about, but we did cover. Evaluation of interpretability. This is something also very important. And these will be not in our exam. So this is not something that is super important to read, but for those who would like to continue research, this is very important. Next one is I would have really loved it if you guys have studied GANs, but you did not. So it would be useless for you guys to study these. Yeah. Decision trees, you already did it, so we already studied it together. I don't think it would be useful to read from this one. Model agnostic methods, this is useful. This is something that is very important. So this is something definitely to read. Now here you'll find global model agnostic methods. I really don't work on these, but for those who are interested in research, you should definitely take a look at it. The book really explains it in a very simple manner, so you should be able to read it very quickly and understand it. Now, the part that will be in the exams is the following: local model agnostic methods. So of course, if you would like to understand Lime better, definitely come here and you will find lots of explanations, much better than what I did in the lecture. And there will be, of course, other algorithms here too. GradCam is not here, right? Yeah, sadly, GradCam is not here, but GradCam is also very important. So you could read about Lime, but the next thing that you guys should read about is SHAP. So SHAP is a very cool algorithm, also doing the same thing as Lime, but it does it in a, I would say, better results. It does give better results, especially for tabular data sets. While working, tabular data is very important, right? So you guys might think that tabular data is something that you guys don't find a lot, but remember, you could convert any image or any word into a vector, and this is what's happening in all the different algorithms, right? For what are they called? Machine learning algorithms. All of them, they convert images and words into vectors, meaning vector data and processing vector data is very important. And this part can be a very good introduction for those who would like to read more about how to process tabular data, right? So just a quick recap. Obligatory reading is SHAP. And evaluation of interpretability and taxonomy of interpretability. Okay. You might think that is a lot of reading, but it's actually not. So basically, after we finish the lab, we will do a quick introduction on how can we read research papers or how can we read research books in a very easy manner. Just to confirm, is Mauricio, is he online? Because he tried to, okay, he is online. Okay, so for some reason, I think you accessed the wrong link and start, right? Okay, cool. So that's cool. Хорошо. I think we could take like another break. Let me just confirm with the what is it called? Victoria. 5, 10, 10. Have we done 1 hour and a half, or did we do 2 hours so far? Regardless of the answer, let's just take a 10 minutes break and come back for the lab. The lab is going to be much quicker than the lecture because this is something very heavy in research, but its application is very simple because the algorithm is just like one click away and you just run the algorithm and get the results, right? So it's not very hard for practice. The most important part is to understand the theory and how could you potentially contribute to this theory for future research, or how can you use this for your models in the future, right? For if you're going for an application that is working on industrial area. We had lots of clients previously with Provectus who really asked us, how can we trust your model? And they just took some edge cases from their data set, from like they were working in construction, and they just took some edge cases and they asked us to explain what the model is seeing to make its decisions, right? So interpretability is still something that is very, very heavily used in industry. For example, Facebook uses it a lot to give you guys the ads. For example, it tells you, why am I seeing, if you just click on any ad on Facebook, it will give you, why am I seeing this ad? You go there and it will give you an interpretation of what the model has used as indications to give you this ad. And from there, you could just try to improve the model's results. So it's just a lot of research about that, right? And lots of applications. If anybody has any more questions, always feel free to ask me. If you do not, but you still have some ideas you would like to cover in this research field, please do think about it, share it with me, discuss it with your friends, and get started with it, right? So it's a very cool field, and research papers are just flying in this area, right? So good luck, and let's come back after 10 minutes. And we're back. Are you guys back? I hope so. Do you guys have any questions?
No.
Nice. And let's open the lab. I think I already put the lab on Moodle. Can you guys, let me check. Yep, I put the lab. Nice. So let's share the screen and get this quickly over with. So this will be a very quick lab. Let me just zoom in a little bit more. Yeah, in this lab, we will speak about interpretability in general. So this is a very, let's say, optional part of the lab. This is for just people who would like to learn about some, just they exist, methods that exists provided by Interpret by Microsoft. So it's a library by Microsoft, very cool one. And it just gives you lots of already explainable or interpretable classification methods, already interpretable regression methods, and of course, means to explain and understand black box classifiers and black box regressors. Black box regressors can be anything from neural networks to any model that exists. And it works very well with sklearn models. So basically, if you have any model from sklearn, you can easily put it here. And all the models that already exist in here can be used exactly the way you use a, what is it called? A sklearn model. So you first start by installing Interpret Microsoft. And this is just a cool data set that you can find online. What we take is the following columns. So the code is pretty generic, as you can see. We split it in train test. This is just some higher level information about how the distribution of classes is compared to the distribution of each single, what is it called, feature. So this is class 1, class 2. We can clearly see that there's a huge class imbalance between 1 and 0. Let's go, for example, work class. Same thing here can be seen. And just gives you the different distributions of the data. This is one way of interpreting it. This is explainable boosting classifier. Is everybody familiar with what is boosting?
No.
Sure. Boosting in machine learning. Ugly. Let's just find a cool image that we can use. So this is one cool way of doing boosting. For example, you take model number 1, it trains on the data, it will make some errors. From these errors, we will calculate weights of sample weights. Basically, this sample was, for example, wrongly classified. We give it a high weight. This one was correctly classified. We give it a low weight. And we send this new, the same data with the new version of the weights to model number 2. The model number 2 will focus more on the errors of model number 1 and then train and again and again and again and again. This will give you an ensemble of models that give you much better results than what you would get from just one model, right? So this is something that is using combining different lower or easier, let's say, simpler classifiers in order to build a more complicated classifier that does a very good job at doing its predictions. I don't think we have enough time to go through all the different boosting techniques. For example, AdaBoost and stuff. AdaBoost is the easiest. So this is what I just described. There are many other gradient boosting, for example. There are many other implementations. There is even one that was created by Yandex, and it's currently the best boosting algorithm. So that's pretty cool also for some people who would like to learn about these kinds of stuff. I did teach a course about these things, but I forgot where it was. So I'm gonna find you like the links to some very cool TDS articles that explain boosting and ensample methods in the most simple form possible and the most beautiful way possible. If you guys are still interested in these things, we could do like a quick like 1 hour something in the next lecture about these things. Because boosting algorithms are very important, right? Let's go back. So this is explainable boosting classifier. And let's see how it's doing. So basically what we are doing in here, we're explaining it in a global manner. The name of the global explainer is EBM, global explainer. So this is a global explainer. Global explainer means it's doing the first 3 scopes of interpretability. If you would like to get more information about that, there's the interpretable ML, interpret ML documentation, which is a very beautiful documentation that explains literally everything you would like to know. Just to see what it's giving you guys, for example, in here, this is just density by, so basically each one of these different values is giving you what is the score, how are the errors, is it giving good results, bad results, and stuff like that. For here, it's doing local explainability, which is like number 4, and it's telling you, for example, for this specific sample, predicted 0, actual 0, why was this correctly predicted? And as you can see in here, this feature was very influential, this was not very influential, this was like negatively influencing, this was positively influencing, the majority of them were positively influencing, so it was classified correctly. So just like this one, if you would like to give it more, it's just you give it this, you give it the data to interpret, and you give it the model to interpret, right? So this is EBM, the model, explain local, so explain your decisions on these data set, and it will give you this beautiful vision. And if you don't want to see it in a visual manner like this one, you will have like a JSON, a dictionary sort information about it in here that you could integrate in your own interface. For example, for those who are working on interpretability models. I remember that there were some companies in Technopark that were very interested in doing this basically, right? So providing interfaces for these models to show an easier interface for these models to show for clients. That's something you guys can do. Another one here is just ROC. So this is just basically area under the curve, and you're getting the ROC. This one, I think, logistic regression, classification tree. So this is just different types of models, and you will see exactly the same things that we have seen before, right? So here we could explain global again. So dark. Well, this is bad. It's either not used or not supported yet. That's bad. So just gives you different cool visualizations to understand what is happening in your data. Sadly, I don't want to run it again. Now, actually, if I run it again, we will have better visuals, but if I do, it will take a lot of time and don't lose the content. Let's just run it again. It shouldn't take a lot of time. It's installing. Pretty quick, right? Let's just continue and maybe it will catch up.
They can share. I'm running it right now, actually.
You're running it? Okay, that's awesome. Can you share?
Right now, yeah.
Good.
Yeah.
Ooh, very well. I can see it here. Nicely done. Yep. So just go down a little bit lower, a bit lower. I think we arrived to yeah, a bit lower, to black box interpretable models, right? Yeah, explaining black box classifiers. The same thing will be for regression, so we don't have to go through regression again. But now, as you guys can see, we are using black box classifiers, and we represent a black box classifier as just a combination between PCA and random forest classifier. So I hope that you guys already know what is PCA. So this is something that I'm sure you guys are all familiar with. Basically, we will find a new hyperspace or dimensionality that reduces or that captures as much of the variance in the data as possible. And based on PCA, and can you just go back a little bit, just to make sure that you guys understand the model, right? So here, do you guys already know how to build pipelines using sklearn? This is also very important for you guys to learn, especially for those who are going to industry. So building pipelines of different steps to create basically a model that is different steps of training. Usually it's very important for natural language processing, but in this case, we're using it for tabular data just to combine PCA and random forest classifier. Random forest classifier is, just as the name suggests, just lots of decision trees trained again and again. And that would give you, so number of estimators means the number of decision trees we're going to build, and you're building an ensemble model based on all of these decision trees. Usually gives much better results than decision tree alone. Now we can just scroll down a little bit. So here we can see, for example, how we are using ROC classifier to use a black box and explain its performance. So now we're explaining its performance. So this is just to see the performance. As you can see, there's nothing really interesting to see, just ROC. The next one would be to explain. So here is line tabular. So as you can see, the name suggests we're using line to explain basically the local decisions of the model. So let's take, for example, any sample, choose a sample. There you go. And this is the results of line. As we have seen in the theory, pretty simple. And the application is extremely straightforward, as you see. Now let's go. Let me see if mine has caught up. Where are we? So explainable black box classifiers. Yeah, actually I did caught up. Thank you, Maxime. I think I could take it up for now. Let's see. So here we go. Yes, Morris sensitivity. Yeah, after this one, we will speak about Morris sensitivity. Morris sensitivity is a very interesting one. I didn't really cover it, but it's very beautiful for research, especially for those who would like to work in. Why is my camera turned off? Let me just make sure it's turned on. Okay. So this is a very interesting technique used by for different applications, and basically it measures the importance of different features for its output. Okay, let's say it in a different word. You have a process. This is not something for neural networks or machine learning. This comes from processes and stuff like that. It was like invented way back in older times. So basically, if you have some process that takes input and gives you output, Morris sensitivity will tell you for this output, how is it sensitive to the input, right? So basically, the importance of the input to the output of a certain process. And this is what you will be getting for this one. For example, each one of these values will have a different mu. Mu is the most important one, so this is the importance. We come here to, for example, the summary, and you will be able to see what are the. So this is one way of saying which features are most important for the model's decisions, right? So this is a method to calculate the importance of features for a black box classifier. We said, how can we calculate the importance of features, for example, for logistic regression? It's basically just the weight of the feature. For decision trees, it's the information gain. If it's a black box classifier or black box model process in general, we can use Morris sensitivity. Partial dependence, useless. These are just different things that you could take a look at.
There was
yeah.
above about the importance of the feature.
Yeah.
The Morris sensitivity in at the start of the notebook, there was something about the importance before this cell.
This one?
I think it's where LR explain global name LR was.
Okay, let me see it. Da-da, da-da.
This one. This one.
This one. Explain global.
And
Yes.
we see overall importance. Is it the same importance
Yes.
measure or?
Exactly.
Okay.
This is for what is called for linear regression and for decision trees. For example, here we will come for decision trees. Cool. So this is the decision tree. It's pretty ugly because it contains a lot of information. The visualization is not perfect. We can say that at least. So this is just the measure. Basically, they're using, they're calculating how useful it is based on where it is being used in the decision tree. And this is one way of measuring the importance of a feature for a certain, what is it called? For the predictions in general. But for open box, right? So for white box or open box, not for black box classifiers. So Morris sensitivity is, again, very cool concept. If you guys would like to use it, for example, for future work on neural networks and understanding neural networks, this is pretty interesting to use. Again, this is just a combination of all of them. We will go quickly through regression models because it's the same thing as we have seen with classification. But here we go. Instead of having classes, we will have the values or the distribution over the values of the response or the y variable. So this is just give you how each feature is correlated basically with the different, with the outputs, right? Here we have an explainable boosting regression. We have linear regression and regression tree. So the regression tree is just a decision tree, but for regression, right? And here we are explaining globally what the model is doing using this EBM method. Here we're explaining it locally. This was very important, not very important, and the intercept was the most important. And here we're explaining the performance. I think the performance is based on, RMSE. Yeah, this is R squared and RMSE. Have you guys studied what is R squared and how does it relate to forgot the name of it, but it's called non-informed model. It should have been like the first lab in machine learning course. No?
I think we studied R square, but I'm not sure on this non-informed model stuff.
Okay, so just you know what R squared is. You know it's a measure for how good a model is, right? So that's already good enough. Understanding it in depth is not really going to change how you're going to use it or interpret it, but that's good. So here we're explaining the performance based again on the R squared and RMSE. Most important parts I would like to see are local explanations. Yes, here. How do they use Lime? Yeah, Lime tabular. There you go. You see the same kind of results based on this one. But you can see that Lime tabular for regression is not the same thing as Lime tabular for classification. So basically there are some changes, but the changes are just instead of having logistic regression, you will have linear regression as a model or as a local model for classification. Now let's go to the most interesting parts, which is using Lime for images and for text, but most importantly for text, right? So here we will take the data set called fetch 20 in use groups. This is very cool data set used always. This is like the toy data set for NLP. And we will take two kind of opposite classes, which are Christianity and atheism, right? So if a text is pro-Christianity, it's clear. If a text is pro-atheism, it's clear. This is just to make sure that we are not working in a very difficult data set. So we're trying to work with something very easy, something that the human being can easily interpret and understand and classify. So for example, here, do you know what is a TF-IDF vectorizer?
No.
We had it in information retrieval.
Yeah, in information
Zero
retrieval.
frequency inverted.
Yes, exactly. So this is just a way to convert the text into a vector. Easy, right? Basically, what we're going to do is just a vectorizer, and it will train on the training data and convert it into training vectors. And then you will just transform it directly on the test data without training on it. You will build this random forest classifier, which is again an ensemble model. You will build this random forest classifier, train it on the training data, and you have the model. This is the accuracy of the model, or the F1 score of the model, 0.92, very good. So the model is doing a very good job. Now let's understand, why is the model doing a very good job? This is the question. So here, for example, we took, okay, so this is the index. We took the sample number 83, and we're trying to see. So this is all you have to do, right? So basically, you create a line text explainer, and you tell it explainer, explain instance. Give it the instance, give it the probability. This is the predict function. Classifier, predict function. This is predict proba because you're not just giving it the prediction directly, but you're giving it the probability provided by the model. So that's like even better information, but not really that much different. And here's just the number of features. If you'd like to increase this one, that would give you a bit more accurate results. And if you'd like to decrease it, then it will give you worse results. And yeah, basically, after you finish all of this beautiful results, you will get the following. Posting, yeah, just like useless, but let's continue. Just visualizations. I like this final visualization, the last one, right? So here you will find the text that was inputted to the model. And here you will find the top 6 features that were captured by the model. So in here, we can see that, for example, I think atheism is the blue one, right? So for example, this NNTP, for the model, it is a very clear sign for atheism. For example, this one, .edu, right? Anything that ends with .edu, usually these are people who will be speaking about the theory of evolution and stuff like that. So it is with atheism. Interestingly enough, for Christianity, you will find the word university. And this is also a very logical thing to do, because university, there are so many universities that are like specific for Christianity, for example, especially in the US, right? So you find many universities that are followed by a religious name, right? So University of, I forgot their names, but are very, very good universities, like, let's see, University Notre Dame, right? I think it's like this. Yeah, University of Notre Dame. So this is something in Indiana. Notre Dame is like, let's say it's another name for the Virgin Mary. So it's something that is very close to Christianity, right? And there are other universities which are also very closely related to the Christianity. And this is why the model has attributed the word university to the concept Christianity. Meaning the model in here is doing a very good job, and it's kind of understanding the text. So it's not just randomly doing its classification, but it's classifying based on correct stuff. But what is bad is, you can see in here, the model did not pick up Darwin's fish as a clear sign of atheism, right? So Darwin is like, let's say the word Darwin is like the most important word in atheism, right? And yet it was not picked up by the model. This could be either a problem from Lime, because Lime is not perfect again, or this could be a problem from the model itself not working very well. Next, for images, it's more or less the same thing. It's a lot of code, very ugly code, because I just like did a very bad job here. But the code in reality is pretty simple, right? So basically, these are just like different values to transform it from, yeah, we're doing it in PyTorch, right? So to take an image, get it into PyTorch sensors, get it in the same format that the model is using. For us, we're using a ResNet 18 model, and this was the pre-processing required by ResNet 18. So we just kept the same things. And here I'm just getting the class to index mapper. So this one is just a JSON that tells you first output is for class human, second output is for class dog, third output is for class tardi. But sadly, since the data set is just huge and contains too many classes, it was not something that I could just put in one dictionary. So we're just going to read it from a JSON and then just take them into dictionaries. So these will be just like dictionaries that map from class to index, from class to label, and from class to index, right? Useless, this is just to read images. Again, useless, useless. Yes, batch predict. This is a very important function. Batch predict is the function that will be called again and again by Lime to make predictions on different samples, right? So Lime will just make random samples, and he will need this batch predict function to make predictions using the model on the images. So in this one, it's pretty easy. You take images, tell the model that we're going to the evaluation setup, create a torch stack or just a torch data set, right, from the images, pre-processed or transformed images, and then you send them into CUDA, send the model into CUDA if it exists. Send the batch through the model, get the output, apply softmax on the output, return the probabilities, always apply detach.cpu.numpy. Why? Detach is just detaching it from the gradients calculations and all of these like complicated internal calculations of of PyTorch. .cpu because we're bringing it back from the GPU, and .numpy because we are not going to use a PyTorch tensor. We're going to use NumPy arrays. At least Lime, of course, it's like a black box interpreter, so it does not care if we're using PyTorch or using something else. So it should be communicating with images and NumPy arrays. So the communications is very basic with minimal with minimal assumptions being made on the content of the model. The rest is just history. So we just create Lime explainer and then explainer.explain instance, give it the instance of interest, give it the classification function. What are the labels that will be predicted, that will be shown basically from it? Useless. Number of samples. This is a very important one. So here is the number of random samples that will be created by the model. And this is the number of images that will be sent for classification function. So the more you put here, the slower the function will be, but the better the accuracy of Lime will be. So here we'll just, of course, this is already done. We have the explanation in a dictionary format. Now what we will be doing is just using this explanation, we will create a mask. So this is just a helper function that will help you basically process the output of this explanation and make it in a beautiful mask that you can easily visualize. So here's the mask. And it's saying that the model has made its decisions based on this region, which is the mouth, the nose, the eyes. And as you can see, since the colors of this whole region is the same, probably our superpixeling method has combined all of this region together, whereas in reality, for example, ResNet only was interested in this pixel alone, not all of these pixels. So this is something that is maybe problematic with with Lime, or it might be a problem from the model. We still don't know that for sure. This is just to create the same code, but with just a bit more visualizations. So this is what I used, for example, for that article to explain that that ResNet, even though ResNet 50 is very big model and it's very accurate, but it makes mistakes, and it makes mistakes because of that region. Now the final part is GradCam. Do you guys want to take a small break and then go through GradCam code, because this is a lot of beautiful code, and I don't want you just to know how to use the code. I want you guys to know how to read the code and understand it. So do you want to take a small break?
Yeah.
Break is always good.
Okay, let's take a 5-minute break and just drink some. Let me just eat some sugars, so my brain would stay functioning. So see you later, guys, or see you soon. Mhm. Just put this in here. And we're back. So I hope you guys are back. I hope you enjoyed your break. And now let's speak about GradCam. So the first class we will speak about is the feature extractor, and then we will speak about this model outputs class. Process image, I don't really think we should speak about it. Also, this is just useless. And then we will speak about the GradCam algorithm in general. This is just for extra for people who would like to read about it. Same thing for this one also. Sorry, it's just extra also for other people who would like to read about this. And this one will be, if somebody would like to read about this and present it to us in the next lectures, you will just have like 15 minutes time and just present to us the research paper for guided backprop value and how it is doing its job and how is it different from GradCam in general. So let's start with the first one, which is the simplest one. This is the feature extractor. So basically, it's a class for extracting activations and registering gradients from targeted intermediate layers. Basically, it has a constructor which takes a model. This is our ResNet, for example, and a target layer. So the target layer is basically what is the, let's go to the model and we'll see what are the target layers. So here we will see, this is VGG, for example, and contains first a sequential features extractor model and an average pooling, adaptive average pooling, and then we will have a classifier. So the classifier, this is what you can think of as our encoder feature extractor, and this is the classifier for the fully connected neural network. As you can see in this first feature extractor or encoder, it's just convolutional layers followed by some ReLU, some X poolings, and convolutional layers repeated again and again and again. And our goal is to basically extract the output, for example, from this layer, or from this layer, or from this layer, right? So we just give it the name of the layer, and he will access it and give us the outputs of that layer. And this is what will happen here. So for example, let's not go for get gradients, let's go for call. So what it will give you is send the, this is not, this is not, yeah, this is the feature extractor, right? So here, when you call it, it will take the X, send it through our beautiful neural network, but layer by layer. So instead of going through the model directly, we are going through each one of the layers one by one. If the name of the layer corresponds to the target layer of interest, we will register the gradients. We will save the gradients of that one at that place, and we will just add that to the outputs, right? So this will be our beautiful outputs, and this is again X. So this is the image or the input image, right? And this is the outputs of the model at a specific layer. And of course, we also register our beautiful gradients. And here, this is the model outputs. It's a class for making a forward pass and first getting the network output, activations from intermediate targeted layers, and the gradients from the intermediate targeted layers. So here we'll take the model, and this is the feature extractor, which is the first part of the model. So taking our beautiful encoder part. So as you can see, we're not taking the model itself, we're taking only the encoder and the target layer of interest. Usually it's just a number. Usually it's just this number, either like 15, 17, whatever it is, right? Let's go back. Here we go. So here, get gradients. Basically, we're just gonna call the feature extractors and get its gradients that were calculated here. And once we call it, how do we call this model? Simple. So basically, we send it through the feature extractors. It gives you the target activations and the final output. Sorry. So here, what we will do, we will just do some reshapes, and we will send the output of the inference model or the encoder to the classifier. Here it is in this case. And this will give you the final output of the model or the classification. And here we get our, what is it called? The targets activations or the feature maps, right? And this gives you the different gradients or the different maps or different matrices of the gradients for that specific map. Pre-processed image, useless code, useless code. This is now the most interesting code. So from here, what we will find is simple. We take the model, we take the interesting layer name, and we use CUDA for the processing. So here we will just take the model, signal to the model. We are in the evaluation setting. We're not going to do any training, and just basically create the class from before. How do we call this one? Simple. So basically, if we send it to CUDA, we're doing it in CUDA. If not, then we're just gonna call the extractor on the input data. Use this again, use this. Yeah, so here, where is he getting the gradients from? Yeah, so here we're just taking the output of the model, making it in one hot encoded vector, and just calculating the back propagation with regards to the gradients. So here, for example, what is happening, this is, kind of forgot this code a little bit. Yeah, this 0 grad and 0 grad is useless. So this is just to make sure that there is nothing really influencing or nothing before this in this code. Nothing is influencing the calculated gradients. And now we're just calculating the gradients again. Here we're just going to the extractor, go to the extractor, getting the gradients, going for the last one, since it's just one image, so the last batch, right? Sending it to CPU, getting the data, then going into NumPy. And features, what is features? Let's go back again. Yeah, this is just the features. Yeah, the features are the different feature maps, right? And this is like -1 just because there's just one sample, right? What we do is targets, send them to the CPU, get all of them and put them in this beautiful format. The weights are going to be the means of grad vals, so the gradient values. And cam is basically going to be the weighted sum. So the weighted sum over the targets window, I, right? So each one, WI multiplied by feature I, let's say. And this is going to be cam. Cam is going to be a beautiful, what is it called? A beautiful feature map with lots of values. Some of them might be negative. So we just apply ReLU. This is just ReLU, right? So maximum between cam and 0 is just ReLU. And here's just for resizing and updating. So just basic pre-processing, post-processing. And that's GradCam, right? So this is what we have seen previously. So here, for example, we're taking target layer name is 36. Layer 36 is the final layer. And the rest is as simple as you can imagine. So just taking this one, reading the image, pre-processing it, sending it to GradCam, and then showing the results. So here we come, we see the results. So for example, here GradCam is not saying that the model is focusing on this region. So the model is mainly focusing on the eyes and the nose. And that is a good model, right? So this is what we expect from the model. Now, another one, for example, let's just, I hope the code is still has finished executing. So now we could just play around with it and see what happens. Let's take, for example, layer number 5. This is our target layer, and see the results. Gonna take some time. Let's see. You see, so when we take a very initial layer, the features that we find interesting in the first layers are not higher level features. So the features that we're finding interesting in the start are just lower level features, such as these edges and all of these things, meaning the feature map is not going to be that, the output of these feature maps is not going to be very interesting for us. This is why we always try to use the final layers. For example, let's not use the final layers, let's use the pre-final layer, and you will not find a big difference between these two, right? So hopefully by the time that we arrived to this layer, we're already in a feature extractor that is a bit abstract, right? So it's not too focused on the details. Let's look here. And we can see that is correct, right? So here, for example, in this feature map, it is giving very good results because it's close to the final one. It's not the final one, but it's very close to the last layers. And the activations in the last layers are very useful for like abstract notions such as eyes and faces and stuff like that. Whereas lower level information or lower level layers are more useful for things such as edges and curves and stuff like that. So this is it. This is the lab. If you guys would like some references, there are tons of them in here, but they're very useful if you guys would like to read more. And for those who would like to present, who would like to go and present next week, you get present to us the guided backprop and basically just the guided backprop model. It's already in the lecture, so if you have seen, it's already explained in the lecture, but we would like you guys to explain it better, right? If you guys don't want to, then it's completely not covered in the course. Do you guys have any questions about the lab so far? No?
There are just a lot of content, and I think it will be necessary to go through the notebook again just after some time.
Exactly. And the lab or the first homework is supremely basic, but it's only thing it's asking you guys to do is go through the lab, copy paste the code, and like put the code in different challenging formats, right? So the code is just going to be copy pasting. As you have seen, it's not really complicated, it's just copy pasting, but if you understand the code, you're going to be able to use it in different situations. The homework is going to be very simple. So the homework is simply, first one, train a from scratch classifier for a specific task, which is dogs versus cats classifier. Second one is to train a transfer learning, basically model. So you take a ResNet 18 and you fine tune it on the same data set and you show the differences in results. And the final task will be basically applying GradCam or Lime, preferably both, on the errors of the model. So what I would like to see is, let's say you take 5 errors from the model and you take 5 correct classifications from the model, and you use GradCam to basically explain to us why or what was the reason for these errors to appear. So this homework is going to be very challenging because you're going to need to understand the lab, but it's very basic. It's just copy pasting, right? So it's pure copy pasting. The idea seems easy. I will already give you guys the Colab link. So it's going to be very well structured and you're just going to need to fill in the values, but it will be quite challenging and certainly interesting for you guys to show off. And I highly recommend that after you submit and you get your grade to, I don't know, put it on your GitHub repo and maybe just do some project about it, right? So something that you can show off during interviews, because it's very important for you when you're during the interview not to let the questions be open-ended, but for you to guide the questions, right? So usually during the interview, if the interviewer does not find any content that is interesting about you to discuss, he will start like just asking random questions. And if he goes to that area, you're probably not going to get the job. But if you force him to ask you questions about the work you have done, something you already know, something that he likes, something that he finds, wow, that's interesting, and he continues asking you that question about it, you have very higher chances of getting the job you want, or getting the PhD, what is it called, a grant you want, and that will open up lots of cool doors for you guys. And that's what I'm seeing with the previous students of this course. So for example, just today and yesterday, a couple of students have asked me on just like more content on some lab that we did, and they're basically going to discuss it in their next interview. So hopefully you guys will find similar patterns to these things, and use this course basically to advance your careers forward, right? Any questions about the lab or the homework? Yeah, homework.
What will be the deadline next week?
I will give you 2 weeks. It's a bit of a challenging one, so I will give you 2 weeks. Is that good?
Yeah.
Nice. Now let's start more of the relaxing part of the lecture, right? So this is gonna be like the final part, and it will be very relaxing, right? So what we will do is the following. We will read 2 articles. The first one is called The Art of Reading a Journal Article Methodically and Effectively. Once we finish this one, we will read another article called The Art of Reading a Research Paper, or research papers. This will be very useful because it will show you tips on how to read a research paper very quickly, right? So in just 5 minutes, you should be able to read any research paper. If you already have good knowledge about the domain, and you understand, for example, what is in object detection, image segmentation, preprocessing, all of these concepts, you know them. Usually every research paper has just like a few key contributions, and understanding how to read a research paper and find these key contributions and answer your questions is gonna save you a lot of time from reading and spending hours scrolling through the internet. So let's take a quick break before we get to this one. Do you guys want a 5 minutes break and we finish early, or do you want like a 10 to 15 minutes break and we finish late?
5 and finish early.
Okay, so let's see you guys in 5 minutes or 4 minutes, and we will finish very soon, right?
By the way, the notebook, the lab notebook will not run, will throw errors if you use GPU runtime.
Oh, really?
Because on the last in the last cell there is no .cpu. There is no allocation to CPU from GPU.
Ah, see, that's where probably my fault. Sorry, because I didn't try it on the GPU yet. But thanks for detecting that. So which area is it?
Not in Gramka, but in Lime images. In
Ah,
Lime
in
images.
Yeah.
Mhm.
Line. This is line, right? Here.
Yes, here were the labels. Let me see. Yeah, here labels equal to list, and there is .detach .numpy. There should be .cpu .detach also.
Yes. .cpu .detach. Yep.
And in 11th line too.
In the 11th line.
Yeah, in 11th line too. Values dot append list.
Yes, very good. Sorry, yep, let's put it here. Much better.
And 12, the second argument. In zip probes.
Detached on numpy. Yep.
Mhm.
Let's send it to CPU and then detach it. Not going to change, but still. Nice. Thank you so much. Let's save it so we don't lose this one. And that's good. Now it can fully run on the GPU. Good. Very impressive. Any other questions maybe from other people? Okay, let's take a quick break and come back for a bit of a relaxation, right? So I think we can come back and try to read it very quickly. So this is what the paper looks like. Usually papers are in like PDF format or something like that, but this one is a bit special. It's like on a website. So just like some background, this is reading scientific literature is mandatory for researchers and clinicians, and mainly because this article is for health related research, right, in the medical field. And just to give you guys some objective to outline a logical and orderly approach for reading scientific manuscript.
Sorry, did you already send the link?
To these things? Nope. Let me send you. One. And yep. So just a small introduction. The introduction will be in this image. This summarizes everything you need to need. So common reasons for reading journal articles. First is to update oneself with progress in a particular field or study. So just to stay updated. The next one is to find a solution for a problem you're working on. To know like the cause or to understand why is something happening to you. Another one is to understand the fundamentals of what's happening. Here, for example, it's for something for like pathologies or like diseases, but for us, it could be generalized to why is the model working? Why is this technique working, or why it's not working? To get an idea for carrying out a research work. So usually this is like the main reason why I read research papers, or why anybody reads research papers, is just to get inspired to do more research on the field. The article has been assigned for you to be read, so by your instructor or something like that, to find support for someone's view. So for example, like to confirm whether using gradient descent is a bad idea or not, you just go on a research paper. And the final one, which is like the most important one, is to impress other people. Very important. Types of journal articles. There are, as the author is saying, there are two types of literature. There is first the primary literature and the secondary literature. Primary literature for us is just whenever there's an article that is presenting a new idea. So this is an article that is completely revolutionary. It's just presenting a new idea that can be applied in different fields. Secondary literature will be just applying the same idea, but in different challenging data sets, for example, right? So for example, you would take, let's say, attention, right? So you would just take a attention-based model and you train it on a specific data set, and you just publish your results on that and tell them that attention for this data set works much better than, let's say, convolutional neural networks. So this is the main difference between primary literature and secondary literature, and you can contribute in both. Of course, primary literature will be valued much more, but secondary literature is also very important because it kind of validates the results of the primary literature. So that's also a very important field of research, and you could do both. Another thing that is very important is to understand what to look for, or how to choose the right article. So first, before we go to how to choose the right article, we'll just see this beautiful flowchart of the first step in choosing an article to read. So what are you looking for? First, if you're looking for ideas for research, this is the type of things you should look at. Mostly it's something that is primary literature based. If you're looking for like diagnosis, therapy, prognosis, this is something that we do not look for, so just completely ignore this one. And if you're looking for a topic overview or updates, this is something that is commonly used. And for that one, you should always cover surveys, right? So usually surveys, for example, if you'd like to, let me see, survey on object detection. Wow. I think I wrote obviously wrong. Horribly wrong. There was something?
There was something new in August, I think.
Nope. Survey. Yep, here it is. Oh, good. Let's not donate because we are cheap people and we do not like to help others. And we read, for example, this is a very good article that you could just read and just to stay updated with what are the current state-of-the-art results for object detection. This is quite old, so it's 2019. Definitely, you're not going to find lots of the best state-of-the-art models right now, but you're going to find lots of very interesting stuff, right? So, for example, you come here, it gives you like an overview of what happened in general. So here, for example, you see Hogg. For those who study best, you have already seen that, right? So you will see Viola Jones, you will see different algorithms for like traditional detection algorithms, the introduction of deep learning and convolutional neural networks, and then from there, everything just started spiraling with RCNN, and then there was SPPNet, which is just like RCNN, but like a bit plus, right? Fast RCNN, faster RCNN, these are different models that we have covered already before. Pyramid networks, we haven't covered them, but I think we just spoke about them like quickly, but we will cover them in very much detail in this course. On the other branch, so there are the two-stage detectors, one-stage detectors. The other branch is the YOLO branch, and here you'll find YOLO, SSD, RetinaNet, and of course YOLO v4, YOLO v5. For example, YOLO v5 version 6, which is like the latest one, and it's getting a lot of buzz these days. And of course, you just come here, gives you like a very cool description of each one of these algorithms. This is why these, what are they called? Survey articles are very useful. It just gives you a global overview of the field. Later on, you will see, for example, here just some comparisons. These are the data sets, metrics. And I really liked also when they spoke about augmentations and stuff. Here they should definitely speak about it soon.
There
that-
was after data set, I think. So.
It was after? Oh, okay, we're not gonna like read this article completely,
Data set.
but yeah, this is like the goal of saying why surveys are very useful. Let's come back. So here, again, if you want to get some idea for research, always read primary research articles. If you would like to go for something that is a bit just to stay updated, you could use surveys. They're very cool. So surveys, I like just YouTube videos for the field, right? How now to start reading an article. This is how to find what the article type you're looking for. Now, how to read an article. Before reading it, you need to know what are the different sections that you will find usually. So first, this is the title, and it will just give you some just like cool or catchy name for the method, right? So usually, for example, fast RCNN, faster RCNN, the name doesn't give you a lot of information, but it just catches your attention. And hopefully they would use some keywords in there, for example, object detection, segmentation, active learning. So usually they just put the keywords that would grab your attention. The abstract is basically a brief overview of the article. Here you will find basically what is the context, what is the proposed method, what is the core idea of the proposed method, what are the results that they are working on, and just a small conclusion, basically saying that our model is the best in the world, or this method works well for our technique. Next is the introduction. This is something that you should not read at first. So this is not something this is not the order of reading. This is just the order of writing, right? The introduction just gives some background information and statements about the hypotheses of the research. So here you will say first paragraph, which is like usually what you find in the first paragraph is the context, and then you will find the problem definition, and then you find what other people are doing to solve that problem. And then you will speak about why you need something else, why these methods are not working, and a paragraph about your method, why does it answer a problem in the other methods, and you just speak about how you evaluate it, and you say a conclusion about what you have just described, right? So this is just like a bit of a larger overview of the article. So the abstract is a very brief overview. This one is a bit of a larger overview, you could say, but it focuses mainly on the background and the context of the work. The methods section, usually there is another section before this one. It's called literature review. In many of the medical fields, they combine introduction with literature review, but for us for computer vision, that is not in medical area. Usually we have introduction and then a separate related works section. Related works section is usually just a description of what are the different methods in the field. For example, if you're working on object detection, you might want to speak about YOLO, you want to speak about RCNNs, and you speak about the differences between them, the speed differences and stuff like that, right? Just like related works description. Methods, here is the most important part of your article, right? So this is the main contribution of your article. And this one details how the study was conducted for them. But for us, usually it's just some mathematical foundation of the model, then some graphs or some diagrams that show the steps of the algorithms if you have the method. Some people would add like an algorithm with step-by-step explanations. Here you will just do everything you would like to do to explain your idea in the most simple ways possible and include as many details as possible. So for example, if we go to faster RCNN, paper, ta-da. It's gonna arrive. Yeah. So here you'll find all the technical details, right? So for example, this is fast RCNN, just some layout of what they would expect. This is region proposal networks. This is the first contribution that they made. So it has a subsection. In this subsection, they will speak about what are anchors, what are the different numbers of anchors they used, translation invariant anchors. These are different types of anchors. Multi-scale anchors as regression references. There are just different versions of this subsection. And next subsection is loss function to train the RPNs. And here is how they are being trained. So you see, they introduced this RPN as a new architecture, and they included first some paragraph about it, just like some description, a general description. And then they spoke about what are the anchors, different types of them, what are the loss functions for each one of these anchors, and how are they being trained. Yeah, these are just like some sharing of the features from RPNs and faster RCNNs. For those who already took the lecture, they know that so faster RCNN is just an RPN in here and a fast RCNN in here, and the same feature extractor from here will be used in here just to save the weights and of course get more training done. And this is just like the final one, which is the 4-step training, alternate training technique to train the whole architecture between fast RCNN and RPNs. And here you'll just find some implementation details. Previously, they were, for example, speaking about K anchors. Here, they will not speak about K anchors. They will speak about 9 anchors, for example, right? So they'll just give you numbers for the values that they have used. Let's go back. So here, as we said, this is the methods section, which details lots of technicality of the paper. The results section, here you will just apply your method on different data sets and compare against other people. So if we come back to the faster RCNN architecture, here you will see, this is just the description of the results, experiments, the experimental setups. This is very important also. They're describing the architecture. So for example, here is the system RPN plus fast RCNN, which is faster RCNN. And this is the backbone, either BGG or ZF. And they just give you the different proposals, region-wise, total, rate, speed, stuff like that. And here is the most important one, is the results. So for the results, we'll see the mean average precision. This is something that we will cover again in the object detection concept. Previously, in the introduction to computer vision, we spoke about mean average precision as just another version of intersection over union, or just another metric for evaluation object detection. But now, in this course, we will go into more detail about it and explain it a bit better. I think we did, I'm not sure if we did it with this course or the other course, so just a bit confused, but we will do it again in this course too. Yeah. So here you can see, for example, this data set, and they show the results on different classes and how they are, of course, better than the competition. Discussion, this is sometimes, in our cases, results and discussions are merged in the same field or in the same section, but for people who are working on medical AI, results are separate, discussion is separate. So in the discussion, usually they just discuss the results. For us in general computer vision, usually just put the table of the results, describe the results, discuss the results, right? Make conclusions directly. For a medical field, usually they just describe the results. These are the results as numbers, nothing there to make conclusions from. Then they go to the discussion and they just make inference from it, right? They just say, oh, maybe this disease is related to this one and correlates with this thing, stuff like that. And of course, there is a final one, which is the conclusion. So references and bibliography, of course, very important, but something is missing here, which is the conclusion. Conclusion is just like a wrap up. It's just another version of the abstract, right? So if you write the abstract, conclusion is going to be like kind of similar, right? So you'll say, in this article, we presented patati patata patata, which is a great one, the best in the field, and gives good results. And we have evaluated it, and it gave good results. And you just put some like words for future works. Now that we know what an article looks like, or what a research paper looks like, let's go for how to decide whether to read it or not. So is the title related to the topic that I'm looking for? Does it have the keywords which I have in mind? If no, then I just skip this article and I do not read it. If it does have the keywords that I'm looking for, I would read the abstract, summary, and conclusion. So it depends on what they have. And ask myself a couple of questions. So do they have clear-cut aims and objectives, well-defined research hypothesis, and are the conclusions precise? So usually for these things, this is something that is very common if you're like trying to read the first time about an object or about a concept. So for example, if you have never heard about object detection, you wouldn't go directly to a paper about faster RCNN. You would stumble a lot on these lower level articles, and this is a very good way to just filter them out. If all of the above is there and it's useful and relevant for what you're looking for, then you can read the entire article. Now, the next one here, they're just going to give you some different description, but we already did that. And I find this one very useful. So these are just some basic statistics commonly used in scientific publications. These are some different ways to make or to present your results. For example, mean, median, range, standard deviation. These are all values that you should always calculate for your results. So the mean, average precision, right? So the mean accuracy over different classes, or the median error, or something like that. Tables, graphs, percentages. And here there are some inferential statistics to say that our method is always better than this method, or something like that. So this is something that you should have studied in statistics course with Professor Suchi. And they're pretty useful, these things, right? Discussion, again, useless. Now, how do you read an article? So first thing you do is to read. They don't have it here. I thought they had it here. Did we miss something? Ah, yes. Nope, not here. Not here. Can't find it. Let me see. Maybe I missed it. Okay, so first thing you read is the title. Sorry, yes. First thing you read is the title. Second thing you read is the abstract. Next thing you read is the conclusion, not the introduction. You go to the conclusion and check it again if it contains the results that you're looking for. The next one you would read is basically the rest. So you would read the introduction, data sets, context, related works, methods. You continue reading it in a sequential manner. So you start with the first part, go to the final part, and then continue with the middle section. This is how you should read a research paper. These are just some final very good questions that you should ask yourself while reading the research paper. And you should always make sure you write about when you are writing a research paper. So for example, what was the article type? Is it an article that is like a first type or primary type, or is it secondary type? The title, who are the authors? These are just some general questions, but introduction, what was the research problem? So this is something that you should define. Any previous studies on this topic? Why are these previous topics not good? Why was this study performed? So basically, what was the problem in previous studies that made you make this new method? What are the aims and objectives of this method? Sometimes what are the challenges of this method? And what was your hypothesis about, right? So saying that our method works best for smaller sized objects, for example, something like that. And you can just go through these questions again. Some of them are relevant, some of them are not. Now this is another article by a professor from School of Computer Science in Fraser University. I think it's with Stanford, right? So it's a Stanford part. It's a Stanford affiliated university. So it's pretty cool article, and it's pretty short. So you can see it's 5 pages. So this is just a brief how-to guide to provide you some instructions on how to read a research paper. Introduction is completely useless. Again, they would just go through the structure of a scientific paper. This is a bit more relevant to us. So for example, you say title, abstract, keywords, introduction, materials and methods, experiment and results, discussion, conclusion, and references. We've already covered all of these. Now what's important is the steps that they provide. So the first step, there are 3 steps, and the first step is to engage with the paper. So begin by just reading the introduction of the abstract, then glance through the pages, just to look at any illustrations, pictures, plots, and finally read the summary and conclusions. Now set the paper aside and ask yourself some questions. What is the paper about? What does it claim to have solved? So these are just some key questions to ask yourself to make sure you understood the paper very well and to help you read it much better. So if you ask yourself these questions, you are engaging with the paper in a way that you do not when you are reading a textbook. The second one is usually the final step in most cases, which is the sieging the paper. So the first one is engage, the second one is siege. He tried to use these kinds of words to make it more engaging, to make the paper more engaging. So if you decided to dig deeper, you need to read the paper with greater care, but at this stage, ignore details such as theorem proofs and stuff like that. So your goal is to basically answer some of the following questions. Does the paper propose a method? In which case, is it sound? Does it work? Some questions again on this ones. So all of these questions, you should try while you're writing to provide answers for them, right? So for example, for introduction, as we have laid out the structure, you should first start with the context, problem definition, current solutions, problems with the solutions, or the current state of the art with the current solutions that are being there, problems about them, and then why your solution, or propose your solution, and why is it important for, why is it different, or why does it solve the problems you have just laid out. And then, of course, you just speak about the rest of the introduction, as we have previously discussed. And the final step is to conquer. So this is like something that is completely not very useful. So it's not something that you always do. So in order to understand the paper, you often need only the first step 1 and 2, and that's it. But if the paper is still not enough to understand, usually you could ask yourself, some of these questions. So these questions are usually for reviewers, so they're not really for somebody who's going to read it to learn from it. And that's it. This is the content that I wanted you guys to see. So this is mainly for those who are going to write a research paper. Writing a research paper is very important. So we could have like a discussion about whether you guys would like to do research or industrial work in the future. But writing research paper is very important for both, especially for those who are data scientists. Currently, for example, where I'm working in, anybody who is like a very high superior in like the hierarchy of the company, they all have PhDs. Of course, since they're kind of old people, PhDs in artificial intelligence did not exist, but PhDs in general and writing articles in general. So for example, some of them, they have PhDs in mechanical engineering and physics and mathematics and stuff like that. But just the fact of doing this research and writing research articles, it just gives you like a new way of thinking, a much better way of organization, of project management, and all of these things, right? So it's going to be pretty useful for you guys for your future, even if you're not going for a research, what's it called? For a research field. It's going to be very useful for even an industrial field, but in the field of data scientists, right? So for software engineers, for example, you're not going to need a PhD or to publish research papers that much. But for data scientists, regardless of whether you're going for a industry or research, you're still going to need research papers, and you're still going to need to have this, unless you want to spend the rest of your life, of course, as just a lower level implementation person. Of course, there are like two kinds of careers. There are just like implementation, people who write the code, and there are the people who decide on the code. And for those who decide on the code, writing research papers is important. Reading research papers is very important. And knowing these like project management skills are also very important. And I hope during this course, you would get like a glimpse on this life and basically how to read research papers and how to write research papers. So thank you guys so much for attending. If you guys have any questions, please feel free to ask them right now. Or for those who would like to ask more private questions, as I'm seeing here right now, you could, I will answer you guys right after the lecture. Anybody has a question? Maybe like a general question about the course in general, the project, the reading research papers as we have seen right now?
Did you already post the link for the homework?
For the homework, no, not yet. I will post it after the lecture. Yeah. Thank you for reminding me. Actually, yeah. Any other questions? If not, then thanks a lot, guys, for attending. I know it's like a weekend and you guys are not spending it having fun. So go out, have fun, and enjoy your weekend. See you guys next week.
Okay, thank you. Bye.
Bye-bye.
Thank you.
Thank you.
Thank you. Goodbye.
Bye-bye.